The universe is vast beyond imagination, filled with countless worlds spinning around distant suns. And we are stuck here, forever. Most people believe that human expansion into the cosmos is inevitable, that it's just a matter of time before we develop the technology to leap between stars like stepping stones across a cosmic river. We see it in every science fiction story, every space documentary, every NASA press release. The assumption is always the same. We'll figure it out eventually. But what if that assumption is wrong? What if the universe itself has constructed an invisible prison around every world, every civilization, every dream of interstellar conquest? What if the very laws of physics that allow stars to shine and planets to form also guarantee that no intelligence can ever truly escape their home system? Today, we're going to explore the most sobering truth in all of science: why humanity is fundamentally, permanently, and absolutely trapped in the solar system forever. Join me as we uncover the iron bars of our cosmic cage, forged not by any enemy, but by the universe itself. Before we begin this journey into our cosmic constraints, I'd love to know, Maitha, what's your current time zone? And what got you interested in space exploration? Share your thoughts in the comments below. Close your eyes and imagine the year 2300. Sleek starships glide effortlessly between worlds, their crews exploring strange new civilizations across the galaxy. Humanity has spread like seeds on the cosmic wind, establishing colonies on thousands of planets orbiting distant suns. This is the future we've been promised, the future we expect. This vision isn't just entertainment. It's become our cultural DNA. From Flash Gordon's rocket ships to Star Trek's warp drive, from Interstellar's wormholes to The Expanse's fusion torches, we've been conditioned to see interstellar travel as humanity's inevitable destiny. It's not a question of if, but when. And why shouldn't we believe it? Look at our track record. In just 70 years, we went from the Wright brothers' first flight to walking on the moon. We've sent robotic ambassadors to every planet in our solar system. We've photographed the surface of Pluto and listened to the sounds of Saturn's rings. If we can do all that, surely traveling to Alpha Centauri is just the next logical step. But here's what's truly fascinating. Every single depiction of interstellar travel in popular culture glosses over the same fundamental problem. They treat the journey between stars like a road trip with better scenery. Captain Kirk orders warp factor 5 as casually as you might ask for the highway to the next town. The writers, the filmmakers, even many scientists seem to assume that the distance between stars is just a larger version of the distance between planets. However, this assumption has infected our thinking so deeply that we've built entire space agencies around it. NASA's long-term plans include missions to Mars, asteroid mining, and eventual expansion beyond the solar system. Private companies like SpaceX explicitly state their goal of making humanity a multiplanetary species, with the clear implication that once we master one planet, we'll master them all. The dream feels so inevitable because it fits perfectly with humanity's greatest story, the story of expansion. We've been spreading across surfaces for our entire existence, first across continents, then across oceans, then into the air, and finally into space. Each barrier that once seemed impossible, the vast Atlantic, the crushing depths of the ocean, the vacuum of space, eventually fell to human ingenuity. So of course, the stars are next. Of course we'll find a way. We always do. But what if this time is different? What if we finally encountered a barrier that no amount of ingenuity can overcome? Let's start with a simple question. How far away is the nearest star? Most people know it's Alpha Centauri, and most know it's about 4.2 light-years away. But what does that actually mean? Let me put it in perspective. Imagine you're standing on a beach in New York while looking out at the Atlantic Ocean. Now, imagine that the entire Atlantic Ocean, all 3,000 miles of it, represents the distance from Earth to Mars. That's already a journey that takes our best spacecraft 9 months to complete. The Atlantic Ocean is Mars. Now, keeping that scale in mind, how far away is Alpha Centauri? If Earth to Mars is the width of the Atlantic Ocean, then Alpha Centauri is approximately 850 times farther away. It's like standing on that same beach in New York and trying to reach a destination that's 850 Atlantic oceans away. But even that comparison fails to capture the true enormity of the challenge. Let's try another approach. The fastest human-made object ever built is the Parker Solar Probe, which reached speeds of 430,000 miles per hour as it whipped around the Sun. At that speed, which required a gravitational slingshot around our star to achieve, it would take 6,200 years to reach Alpha Centauri. That's longer than all of recorded human history. The Voyager 1 spacecraft, humanity's most distant messenger, was launched in 1977. It's now flying through interstellar space at about 38,000 miles per hour. If it were aimed at Alpha Centauri, which it's not, it would arrive in about 75,000 years. That's 3 times longer than modern humans have existed. Let me give you one more way to think about it. If you could fold a piece of paper in half 42 times, it would reach the moon. If you could fold it 51 times, it would reach the Sun. To reach Alpha Centauri, you'd need to fold it 54 times. That's not just a little bit farther, it's exponentially farther. And Alpha Centauri isn't just the nearest star. It's also one of the most boring. It's a triple star system with no known planets that could support life. The nearest potentially habitable world is Proxima Centauri b, which orbits the smallest, most violent star in the system. It's probably tidally locked, meaning one side faces eternal day while the other faces eternal night. It's likely been stripped of its atmosphere by stellar radiation. The truly interesting stars, the ones with confirmed Earth-like planets, the ones that might actually harbor life, are dozens or hundreds of light years away. If Alpha Centauri is 850 Atlantic oceans away, these destinations are hundreds of thousands of Atlantic oceans away. This is the first hint that something is fundamentally different about interstellar travel. The scale isn't just big, it's incomprehensibly vast. But scale alone isn't what traps us. After all, humans have overcome seemingly impossible distances before. Ancient Polynesians navigated thousands of miles of open ocean in outrigger canoes. The scale is daunting, but it's not insurmountable. No, what traps us is something far more fundamental. The universe has a speed limit. Every highway has a speed limit, and so does the universe. But unlike the speed limits on our roads, which are set by human lawmakers and can be changed by human lawmakers, the cosmic speed limit is built into the very fabric of reality itself. It's not a suggestion or a guideline. It's an absolute, unchangeable law of nature. That speed limit is the speed of light, 186,282 miles per second, or about 670 million miles per hour. And here's the crucial point that most people miss. Nothing with mass can ever reach this speed. Not 99.9% of light speed, not 99.99% of light speed, not even 99.99% of light speed. The closer you get to light speed, the more energy you need to go faster, and that energy requirement increases exponentially without limit. This isn't a technological limitation, it's a fundamental property of space-time itself. Albert Einstein discovered this in 1905, and every experiment since has confirmed it. The speed of light isn't just the speed that light travels, it's the speed that causality itself propagates through the universe. It's the speed at which cause and effect can travel from one point to another. Think of it this way. The universe is like a vast ocean, and the speed of light is like the speed of sound in water. You can't make sound travel faster than the speed of sound, no matter how much energy you put into it. Similarly, you can't make matter travel faster than the speed of light, no matter how powerful your engines become. But let's say we could somehow approach the speed of light. Let's imagine we built a spacecraft that could travel at 90% of light speed, an achievement that would require more energy than humanity has ever produced in its entire history. Even at this impossible speed, the journey to Alpha Centauri would take over 4.5 years. The journey to more interesting star systems would take decades or centuries. You have a burr, and that's traveling at 90% of light speed. which is physically impossible with any known or theoretical propulsion system. The energy required to accelerate even a small spacecraft to such speeds would be equivalent to the entire energy output of the sun for several years. Here's where it gets worse. The speed of light isn't just a speed limit, it's also a communication limit. Even if we could somehow send a message to another star system, perhaps by radio or laser, that message would take years to arrive. A conversation with colonists on Alpha Centauri would involve an 8-year delay between question and answer. A conversation with colonists around more distant stars would involve delays of decades or centuries. This means that even if we could somehow establish interstellar colonies, they would be effectively isolated from Earth forever. They couldn't participate in Earth's economy, Earth's culture, or Earth's civilization. They would be, for all practical purposes, completely alone. The speed of light creates what physicists call a light cone, a boundary around every point in space-time, beyond which cause and effect cannot travel. Earth exists in its own light cone, and every other star system exists in its own light cone. These light cones barely overlap, even over cosmic timescales. This is why SETI, the search for extraterrestrial intelligence, faces such a fundamental challenge. Even if we detected a signal from another civilization, even if we could decode their message and send a reply, the conversation would unfold, over time, scales longer than human lifespans. It would be like trying to have a conversation with someone, where each exchange takes longer than a human generation. The speed of light doesn't just limit our ability to travel to other stars. It limits our ability to even communicate with other stars in any meaningful way. It creates a kind of cosmic quarantine around every world, every civilization, every dream of galactic community. But surely, you might think, there must be loopholes. Surely, the universe, in its infinite creativity, has left us some way around this fundamental limitation. Surely, someone as clever as humanity can find a way to break free. This is where our journey into the prison walls of physics truly begins. Because as we're about to discover, the speed of light is just the first bar in our cosmic cage. The real barriers, the ones that make interstellar travel not just difficult, but fundamentally impossible, are written even deeper into the mathematical structure of reality itself. Let's talk about energy, not the abstract concept you learned about in high school physics, but the cold, hard mathematical reality that governs every dream of interstellar travel. When you accelerate any object, you're adding energy to it. Push a shopping cart, and you're adding kinetic energy. Fire a rocket, and you're adding a tremendous amount of kinetic energy. This seems straightforward until you approach the speed of light, where the mathematics become absolutely brutal. Here's the equation that crushes all our interstellar dreams. As you accelerate an object closer and closer to the speed of light, the energy required increases exponentially, not linearly, exponentially. The difference is catastrophic. Let me show you what this means with real numbers. Imagine we want to send a spacecraft to Alpha Centauri, not a massive spacecraft. Let's be modest. Let's say we want to send a probe the size of a small car, weighing about 1,000 kilograms. And let's say we want it to reach 10% of the speed of light, fast enough to reach Alpha Centauri in 42 years instead of 75,000 years. The energy required for this seemingly modest goal is approximately 4.5 quark, 10 circumflex, 18 joules, hoc. That's 4.5 quintillion joules. To put that in perspective, that's about 1,250 terawatt-hours of energy, roughly equivalent to the entire annual energy consumption of the United States. The entire United States, for 1 year, to send a car-sized probe to our nearest stellar neighbor at 10% of light speed. But wait, it gets worse. Let's say we want to go faster. Let's aim for 50% of light speed, which would get us to Alpha Centauri in less than 9 years. The energy requirement doesn't just increase by a factor of 5, it increases by a factor of about 30. We'd need the equivalent of the entire world's energy production for several years. And if we want to approach 90% of light speed, the energy requirement becomes approximately equivalent to the mass energy of the probe itself. According to Einstein's famous equation, E equal mech z. We'd need to convert matter directly into energy with perfect efficiency, something that's theoretically possible, but practically impossible. This is what physicists call the relativistic energy barrier, and it's not a technological problem. It's a fundamental law of nature. No matter how advanced our technology becomes, no matter how clever our engineers, we cannot escape the mathematics of special relativity. But let's imagine, for a moment, that we somehow solved the energy problem. Let's say we discovered a way to harness the entire energy output of our sun for our spacecraft. Surely, that would be enough energy to accelerate a probe to near light speed. Actually, no. Here's where the mathematics become truly diabolical. As your spacecraft approaches the speed of light, something strange happens from the perspective of an outside observer. The spacecraft's mass begins to increase, not its rest mass that stays the same, but its relativistic mass, the mass that determines how much energy you need to accelerate it further, increases without limit. This creates a feedback loop of impossibility. The more energy you put into accelerating the spacecraft, the more massive it becomes from the perspective of spacetime, which means you need even more energy to accelerate it further. It's like trying to climb a mountain that grows taller the higher you climb. The mathematical limit is clear and absolute. To accelerate any object with mass to the speed of light would require infinite energy, not just a lot of energy, infinite energy. And since the universe contains finite energy, this is impossible by definition. Even if we could somehow harness the gravitational energy of black holes, even if we could tap into the quantum vacuum itself, even if we could violate the laws of thermodynamics, we still couldn't overcome this fundamental barrier. The mathematics are as unchangeable as the value of pi. This is why even the most optimistic physicists, the ones who speculate about antimatter drives and fusion ramjets, typically talk about achieving maybe 10% to 20% of light speed, not because they lack imagination, but because they understand the mathematics. They know that the energy requirements become prohibitive long before you approach anything resembling the speed of light. The cruel irony is that the universe is constructed in such a way that the speed you need to make interstellar travel practical is precisely the speed that the universe makes impossible to achieve. It's as if the cosmos has been designed to keep every civilization trapped in their own local neighborhood forever. The energy problem is just the beginning. There's another aspect of relativity that makes interstellar travel even more impossible: the mass-energy paradox. Here's what happens when you try to accelerate any object with mass to the speed of light. Its relativistic mass approaches infinity. This isn't just a mathematical curiosity. It has profound physical consequences. Think about it from the perspective of space-time itself. As your spacecraft accelerates, it begins to curve space-time around it more and more dramatically. At extremely high speeds, your spacecraft would begin to exhibit gravitational effects similar to those of a black hole. The faster you go, the more you warp the fabric of reality itself. This creates a fundamental paradox. The very act of trying to escape your local region of spacetime causes you to distort spacetime so severely that you become trapped within your own gravitational field. You become a prisoner of your own mass energy. But there's an even more subtle trap hidden within the mathematics. As your spacecraft approaches light speed, time dilation kicks in. From the perspective of the crew aboard the spacecraft, time passes normally, but from the perspective of Earth, time aboard the spacecraft slows down dramatically. This might seem like a good thing. After all, if time passes slowly enough aboard the spacecraft, even a journey of thousands of years might feel like months to the crew. But time dilation creates its own prison. The faster you travel, the more you become disconnected from the universe you're trying to explore. At 90% of light speed, a journey that takes 10 years from Earth's perspective would feel like only 4.4 years to the crew. But here's the catch. While the crew experiences 4.4 years, the rest of the universe ages 10 years. Over is proves ever that be more visir. Any civilization they left behind continues to evolve, continues to advance, continues to change. If they ever return home, they would find a world that has moved on without them. They would be temporal exiles, displaced, not just in space, but in time itself. The universe they sought to explore would have changed beyond recognition during their journey. This is the mass-energy paradox in its full, cruel glory. The faster you try to travel through space, the more you become isolated from the time stream of the universe itself. You don't just become trapped by distance, you become trapped by time. Albert Einstein never intended to imprison humanity. When he published his special theory of relativity in 1905, he was simply trying to understand how light behaves. But in solving that puzzle, he accidentally discovered the bars of our cosmic cage. The cage is built from the most fundamental properties of space-time itself. It's not made of matter or energy, it's made of geometry. The shape of reality itself prevents us from escaping our local region of the universe. Here's how the cage works. Space-time is not the empty void we imagine. It's a dynamic, flexible medium that responds to the presence of mass and energy. When you accelerate a spacecraft, you're not just pushing it through empty space, you're forcing it to interact with the geometric structure of space-time itself. The faster you go, the more dramatically space-time responds. At low speeds, this response is negligible, but as you approach the speed of light, space-time begins to resist your motion with increasing intensity. It's not friction in the traditional sense, it's the geometry of reality itself, pushing back against your attempts to violate its fundamental structure. This resistance manifests in several ways. First, there's the energy requirement we've already discussed, but there's also time dilation, length contraction, and the increase in relativistic mass. These aren't separate phenomena, they're different aspects of the same geometric constraint. From the perspective of space-time, what we call acceleration is actually a rotation through the four-dimensional geometry of space-time. When you accelerate through space, you're also rotating through time. The faster you move through space, the slower you move through time, and vice versa. This four-dimensional rotation has a maximum limit, the speed of light. Beyond that limit, the mathematics break down completely. You cannot rotate past 90 degrees in space-time, just as you cannot rotate past 90 degrees in ordinary space without changing direction entirely. But Einstein's cage has even more subtle constraints. The theory of general relativity, which Einstein published in 1915, reveals that massive objects don't just move through space-time, they curve it. The sun doesn't pull planets toward it with some mysterious force called gravity. Instead, the sun curves space-time in such a way that planets follow the straightest possible paths through that curved geometry. This curvature effect becomes extreme at high speeds. A spacecraft traveling at near light speed would curve space-time around itself so dramatically that it would begin to trap light, and therefore information, within its own gravitational field. The spacecraft would become a kind of black hole, cut off from the rest of the universe, not just by distance, but by the fundamental geometry of space-time itself. There's another, even more profound constraint hidden within Einstein's equations. The speed of light isn't just the maximum speed for matter, it's the maximum speed for causality itself. It's the speed at which cause and effect can propagate through space-time. It's the speed at which cause and effect can propagate through space-time. This means that even if we could somehow circumvent the energy requirements, even if we could somehow avoid the mass-energy paradox, we still couldn't travel faster than light without violating the fundamental logical structure of the universe. We would be trying to arrive at our destination before we left our origin, creating paradoxes that would tear apart the fabric of causality itself. Einstein's cage is perfect because it operates at multiple levels simultaneously. It constrains us through energy requirements, through mass-energy relationships, through time dilation, and through the fundamental structure of causality itself. Even if we could somehow solve one constraint, the others would still hold us prisoner. The cage is also universal. It applies to every civilization, every intelligence, every dream of interstellar expansion, anywhere in the universe. The laws of physics don't care about our ambitions or our technology. They apply equally to every atom, every planet, every star system in the cosmos. This universality has profound implications. It means that not only are we trapped in our solar system, but every other civilization in the universe is trapped in their solar system as well. The universe is filled with islands of intelligence, each surrounded by an ocean of impossible distance, each forever isolated from the others by the iron laws of relativity. Einstein's cage doesn't just prevent us from traveling to other stars. It prevents us from ever truly knowing if there are other civilizations out there, even if they exist, even if they're trying to communicate with us. The vast distances and the speed of light limit ensure that we might never find each other. We are not just trapped in our solar system, we are trapped in our own cosmic loneliness. But surely, you might think, there must be some loophole. Surely, Einstein's equations allow for some exotic solution, some clever workaround that could free us from our prison. After all, the equations themselves seem to permit strange phenomena like wormholes and warp drives. This is where our journey takes us next, into the realm of exotic physics, where desperate minds have searched for escape routes from Einstein's cage. But as we're about to discover, every apparent loophole comes with its own impossible requirements, its own fundamental barriers, its own reasons why the universe refuses to let us go. Let's start with the technology that got us into space in the first place. Chemical rockets. These magnificent machines, with their columns of fire and thunder, represent humanity's first serious attempt to escape the gravitational embrace of Earth. They're also our first lesson in the fundamental limitations that will plague every propulsion system we'll ever develop. Chemical rockets work by burning fuel with an oxidizer, creating hot gases that expand rapidly and shoot out the back of the rocket at high speed. It's Newton's third law in action. For every action, there's an equal and opposite reaction. Push gas one way, and the rocket goes the other way. The problem is efficiency. Chemical rockets are spectacularly inefficient. The space shuttle, one of the most advanced chemical rocket systems ever built, could barely reach orbit, and orbit is just the beginning of any interstellar journey. Getting to orbit requires a velocity of about 17,500 miles per hour. Getting to Alpha Centauri in a reasonable time frame requires velocities of tens of millions of miles per hour. But the real problem with chemical rockets isn't their maximum speed, it's their fuel requirements. To understand this, you need to understand something called the tyranny of the rocket equation. This equation, formulated by Konstantin Tsiolkovsky in 1903, describes the relationship between a rocket's mass, its fuel consumption, and its final velocity. The rocket equation reveals a cruel truth. To go twice as fast, you don't need twice as much fuel. You need exponentially more fuel. And most of that fuel is spent accelerating the fuel itself, not the payload. Let me give you a concrete example. The Saturn V rocket, which carried astronauts to the moon, weighed 6.2 million pounds when fully fueled. Of that enormous mass, only 50,000 pounds, less than 1%, was the actual spacecraft that went to the moon. The rest was fuel and fuel tanks. Now imagine trying to reach Alpha Centauri with chemical rockets. Even if we could somehow build a chemical rocket capable of reaching 1% of the speed of light, which we can't, the fuel requirements would be astronomical. We would need a rocket with a mass equivalent to several planets, just to send a small probe to our nearest stellar neighbor. The numbers are so absurd that they cross the line from difficult to impossible. You literally cannot build a chemical rocket capable of interstellar travel, no matter how much money you spend, no matter how clever your engineers, no matter how advanced your materials. The physics simply don't allow it. But chemical rockets taught us something important. The fundamental challenge of interstellar travel isn't engineering, it's physics. Every propulsion system must obey the same basic laws of conservation of momentum and energy. Every system must carry its own fuel, which means every system must accelerate not just the payload, but the fuel itself. This is why chemical rockets can barely get us to Mars. Mars is right next door in cosmic terms, just a few light minutes away. Even with perfect efficiency, even with unlimited funding, chemical rockets would take centuries to reach the outer planets of our own solar system. Interstellar travel is completely beyond their capabilities. The failure of chemical rockets forced engineers to think beyond combustion. If burning fuel in a combustion chamber couldn't provide enough energy, maybe we needed to look at more energetic processes. Maybe we needed to harness the power of the atomic nucleus itself. When nuclear fission was first discovered in 1938, it must have seemed like the answer to every propulsion problem. Here was a process that released millions of times more energy than any chemical reaction. Surely this would be enough to power interstellar missions. The promise of nuclear propulsion seemed limitless. Project Orion, conceived in the 1950s, proposed using nuclear explosions to propel spacecraft. The idea was beautifully simple. Detonate nuclear bombs behind a spacecraft, use a massive shock absorber to cushion the crew, and ride the explosions like a surfer rides a wave. The numbers were impressive. An Orion spacecraft could theoretically reach 5% of the speed of light, cutting the journey time to Alpha Centauri to less than a century. For the first time, interstellar travel seemed genuinely possible. But Project Orion revealed new problems that would plague every nuclear propulsion system. First, there was the engineering challenge of building a spacecraft that could survive repeated nuclear explosions. The shock absorber alone would need to be the size of a skyscraper, and it would need to absorb the energy of hydrogen bombs without failing. Second, there was the fuel problem. Even nuclear fuel has mass, and even the most efficient nuclear reactions convert only a small fraction of matter into energy. To reach 5% of light speed, an Orion spacecraft would need to carry thousands of nuclear bombs, each one adding to the total mass that needs to be accelerated. Third, there was the radiation problem. Nuclear propulsion systems produce tremendous amounts of radiation, both neutrons and gamma rays. Any crew would need massive shielding, which adds even more mass to the spacecraft. The radiation would also damage the spacecraft itself, potentially causing critical systems to fail during the decades-long journey. The more engineers studied Project Orion, the more problems they discovered. The spacecraft would need to be enormous, larger than any structure ever built. The nuclear fuel would need to be manufactured in quantities that exceeded the entire global nuclear arsenal. The launch would irradiate large portions of Earth's atmosphere. Eventually, Project Orion was abandoned, but the dream of nuclear propulsion lived on. Engineers proposed nuclear ramjets that would scoop up interstellar hydrogen and fuse it for propulsion. They designed fusion rockets that would use magnetic fields to contain nuclear reactions. To contain nuclear reactions, they imagined nuclear pulse drives that would use tiny fusion explosions for thrust. To contain nuclear renta below from nuclear ranjan. Every design faced the same fundamental problems. Nuclear reactions, for all their power, are still limited by the laws of physics. Even the most energetic nuclear process, the complete fusion of hydrogen into helium, can only convert about 0.7% of the fuel's mass into energy. That's millions of times more efficient than chemical reactions, but it's still nowhere near the efficiency needed for practical interstellar travel. The fuel mass problem becomes clear when you run the numbers. To accelerate a spacecraft to 10% of light speed using nuclear propulsion, you need a fuel mass that's several times the mass of the spacecraft itself. To reach higher speeds, the fuel requirements increase exponentially. There's also the problem of fuel collection. Interstellar ramjets sound elegant in theory. Why carry fuel when you can scoop it up along the way? But the reality is that interstellar space is nearly empty. The density of hydrogen between stars is about 1 atom per cubic centimeter. To collect enough fuel for fusion, you'd need a scoop with an area measured in square kilometers. The engineering challenges are staggering. The magnetic fields needed to contain fusion reactions are enormously powerful and require superconducting coils cooled to near absolute zero. The radiation from fusion reactions would destroy any conventional materials within hours. The neutron flux would make the spacecraft itself radioactive. But perhaps the most fundamental problem with nuclear propulsion is that it's still not energetic enough. Even with perfect efficiency, even with unlimited fuel, nuclear reactions simply don't release enough energy to make interstellar travel practical. The energy density of nuclear fuel is impressive compared to chemical fuel, but it's still pathetic compared to what physics actually allows. This realization led to the most ambitious propulsion concept ever seriously proposed: antimatter propulsion. If nuclear reactions weren't energetic enough, maybe we needed to look at the most energetic process possible in physics: the complete annihilation of matter and antimatter. Antimatter represents the theoretical pinnacle of energy storage. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass into pure energy, according to Einstein's E=mc². This is the most efficient energy conversion process possible in physics. There is literally nothing more energetic. The numbers are staggering. 1 kilogram of antimatter, when annihilated with 1 kilogram of matter, releases the same amount of energy as 43 million tons of TNT. That's more energy than the largest nuclear bomb ever detonated. A single gram of antimatter contains enough energy to power a city for weeks. For spacecraft propulsion, antimatter seems like the ultimate solution. An antimatter rocket could theoretically achieve significant fractions of light speed. The exhaust velocity would be the speed of light itself, providing maximum efficiency according to the rocket equation. Finally, it seemed we had found a way to break free from our solar system. But antimatter propulsion faces problems that go far beyond mere engineering challenges. These are fundamental barriers that make antimatter not just difficult to use, but effectively impossible. First, there's the production problem. Antimatter doesn't exist naturally on Earth. It has to be manufactured, and manufacturing antimatter is the most inefficient process in human technology. The current world record for antimatter production is about 10 trillion antiprotons per hour, created at enormous expense in particle accelerators. To put this in perspective, at current production rates, it would take 10 billion years to produce a single gram of antimatter. That's longer than the current age of the universe. Even if we could somehow increase production efficiency by a factor of 1 billion, it would still take decades to produce enough antimatter for a single interstellar mission. The energy cost of antimatter production is equally prohibitive. Current methods require about 10 billion times more energy to produce antimatter than the antimatter itself contains. This isn't just inefficient, it's so inefficient that it violates the basic economics of energy production. You'd need to harness the entire energy output of the sun for centuries just to produce enough antimatter for one spacecraft. But let's imagine we somehow solved the production problem. Let's say we discovered a way to manufacture antimatter efficiently, perhaps by mining it from the quantum vacuum or collecting it from cosmic rays. We'd still face the storage problem. Antimatter cannot be stored in any conventional container because it annihilates with ordinary matter on contact. The most advanced storage concepts use magnetic fields to suspend antimatter in a perfect vacuum, but these systems are incredibly complex and energy-intensive. The magnetic fields themselves require enormous amounts of power to maintain, and any failure would result in the instant annihilation of the entire fuel supply. Even if we could somehow store antimatter safely, we'd face the propulsion problem. An antimatter rocket engine would need to precisely control the annihilation of matter and antimatter, converting the resulting energy into thrust. The energy densities involved are so extreme that no known material could withstand them. The rocket nozzle would need to be made of pure magnetic fields, shaped and controlled with impossible precision. The radiation problem is equally severe. Antimatter annihilation produces intense gamma rays and high-energy particles that would irradiate everything within miles of the spacecraft. Any crew would need shielding so massive that it would defeat the purpose of using antimatter in the first place. Intro would need shielding so massive that it would defeat the purpose of using antimatter in the first place. But perhaps the most fundamental problem with antimatter propulsion is that it doesn't actually solve the core challenge of interstellar travel. Even with perfect antimatter rockets, even with unlimited fuel, the journey to Alpha Centauri would still take years. The journey to more distant stars would still take decades or centuries. Remember, antimatter doesn't let you exceed the speed of light. It just lets you approach it more efficiently. And as we've seen, approaching the speed of light creates its own problems. time dilation, length contraction, and the exponential increase in energy requirements as you get closer to the ultimate speed limit. There's also the targeting problem. At the speeds enabled by antimatter propulsion, navigation becomes extraordinarily difficult. A spacecraft traveling at 50% of light speed would have only seconds to detect and avoid obstacles. The Doppler shift would make stars appear to change color and position. The crew would be flying blind through a universe transformed by relativistic effects. The deceleration problem is equally challenging. It's relatively easy to accelerate a spacecraft to high speeds. You just need enough fuel and energy, but slowing down at the destination requires just as much fuel and energy as accelerating in the first place. An antimatter spacecraft would need to carry twice its fuel load, half for acceleration and half for deceleration. This doubles the already impossible fuel requirements and makes the engineering challenges even more severe. You'd need to store antimatter safely for decades or centuries during the journey, maintain perfect engine efficiency throughout the mission, and somehow navigate across interstellar distances with precision measured in millions of miles. When you add up all these problems, production, storage, propulsion, radiation, navigation, and deceleration, antimatter propulsion reveals itself as what it truly is, a beautiful theoretical concept that cannot be implemented in practice. It's a mirage that appears achievable from a distance, but dissolves into impossibility when you examine the details. The failure of antimatter propulsion represents the end of the road for conventional rocket technology. We've now explored chemical rockets, nuclear rockets, and antimatter rockets, the full spectrum of energy sources available to physics. None of them can provide practical interstellar travel, but human ingenuity doesn't give up easily. If conventional propulsion won't work, maybe we need to think beyond conventional physics. Maybe we need to explore the exotic realms of theoretical physics, where space and time themselves can be manipulated. Maybe we need to look for loopholes in the fundamental laws of the universe. This is where our journey takes us next, into the realm of wormholes, warp drives, and quantum entanglement, into the physics of desperation, where every theoretical possibility is explored in the search for an escape route from our cosmic prison. When Albert Einstein and Nathan Rosen first described what we now call wormholes in 1935, they weren't trying to solve the problem of interstellar travel. They were exploring the mathematical consequences of general relativity, following the equations wherever they led. What they discovered was a theoretical structure that seemed to offer the ultimate shortcut through space-time, a tunnel that could connect distant regions of the universe. The concept is elegantly simple. If space-time can be curved by mass and energy, why can't it be curved so severely that it folds back on itself? Imagine a flat sheet of paper representing space-time. Now imagine folding that paper so that two distant points touch. A wormhole would be like poking a hole through both layers, creating a shortcut that bypasses the long journey across the paper's surface. For decades, wormholes represented the holy grail of interstellar travel. Here, finally, was a way to travel vast distances without actually traveling through space. You could step into a wormhole on Earth and emerge moments later near Alpha Centauri, or Vega, or any other star system. The journey time would be measured in minutes rather than millennia. The mathematics of wormholes are beautiful and consistent with general relativity. The equations describe structures called Einstein-Rosen bridges that connect different regions of space-time through higher dimensional tunnels. From a theoretical perspective, wormholes are not just possible, they're inevitable consequences of the geometry of space-time itself. But there's a problem that destroys every wormhole fantasy. They're catastrophically unstable. The mathematics that allow wormholes to exist also require them to collapse almost instantly. The moment any matter or energy, including light, enters a wormhole, the tunnel begins to contract. The contraction happens so rapidly that the wormhole pinches off before anything can travel through it. It's like trying to run through a closing door that closes faster than you can run. To keep a wormhole open, you need something called exotic matter, matter with negative energy density. This isn't just rare matter or unusual matter. It's matter that has fundamentally different properties from anything that exists in our universe. Exotic matter would have negative mass, negative energy, and would violate several fundamental laws of physics. The energy requirements for creating exotic matter are beyond astronomical. To keep a wormhole open long enough for a human to pass through, you'd need exotic matter with negative energy equivalent to the mass energy of the sun, and you'd need to maintain this exotic matter in a perfectly stable configuration indefinitely. But even if exotic matter existed, even if we could somehow create and control it, wormholes would still be useless for interstellar travel. Here's why. You can't create a wormhole endpoint anywhere you want. We can't create a wormhole endpoint anywhere you want. The other end of the wormhole has to already exist, and the only way to create it is to transport it there through normal spacetime. This creates a paradox. To use a wormhole to travel to Alpha Centauri, you'd first need to send one end of the wormhole to Alpha Centauri using conventional propulsion. But if you could send something to Alpha Centauri using conventional propulsion, you wouldn't need the wormhole in the first place. The wormhole paradox gets worse when you consider the implications for causality. If wormholes could be created and controlled, they would inevitably lead to time travel paradoxes. You could send information backward in time, potentially altering the past and creating logical contradictions that would tear apart the fabric of space-time itself. Recent research has suggested that the universe may have built-in protection against these paradoxes. The same quantum effects that create Hawking radiation around black holes would probably destroy any wormhole that threatened to create a time paradox. The universe seems to actively prevent the creation of structures that could violate causality. There's also the traversability problem. Even if stable wormholes existed, even if they could be created without exotic matter, passing through them would likely be fatal. The tidal forces near a wormhole would be enormous, stretching and compressing any traveler beyond the limits of human survival. The radiation generated by the wormhole's collapse would be lethal. The more physicists study wormholes, the more problems they discover. The quantum effects that might stabilize wormholes also make them incredibly dangerous. The energy required to create them is impossible to obtain. The exotic matter needed to maintain them probably doesn't exist. But perhaps most fundamentally, wormholes don't actually solve the problem they're supposed to solve. They don't provide a way to travel faster than light. They provide a way to travel through folded space-time. The journey through a wormhole would still take time, and information traveling through a wormhole would still be limited by the speed of light. Wormholes represent the first great false hope of exotic physics. They promise easy interstellar travel, but they deliver only mathematical curiosities that cannot be implemented in the real world. They're like theoretical bridges that exist only on paper, spanning impossible chasms with materials that don't exist. The failure of wormholes forced physicists to explore even more exotic concepts. If you can't create shortcuts through space-time, maybe you can manipulate space-time itself. Maybe you can create a bubble of space that moves faster than light, carrying a spacecraft along with it. This is the promise of the Alcubierre drive, a concept that seems to offer everything wormholes promised, but with even more impossible requirements. In 1994, physicist Miguel Alcubierre published a paper that sent shockwaves through the physics community. He had found a solution to Einstein's field equations that seemed to permit faster-than-light travel without violating the laws of relativity. The concept was brilliant. Instead of moving through space, you would move space itself. The Alcubierre drive works by contracting space-time in front of a spacecraft and expanding it behind. The spacecraft sits in a bubble of flat space-time that moves faster than light, carrying the ship along with it. From the perspective of the crew, they never exceed the speed of light locally. From the perspective of the outside universe, they arrive at their destination faster than light could travel through normal space. It's like being on a moving walkway at an airport. You're walking at normal speed relative to the walkway, but the walkway itself is moving, so you reach your destination faster than you could whole by walking alone. The Alcubierre drive is a moving walkway made of space-time itself. The mathematics are elegant and consistent with general relativity. The space-time geometry described by Alcubierre's equations doesn't violate any known laws of physics. For a brief moment, it seemed like humanity had found its escape route from the solar system. But the Alcubierre drive comes with requirements that are not just difficult, they're impossible. First, there's the energy requirement. To create an Alcubierre drive capable of faster-than-light travel, you need negative energy density equivalent to the mass energy of the planet Jupiter. Not Jupiter's mass energy, which is Jupiter's mass multiplied by the speed of light squared. That's about 1.9 GWh 10 circumflex 47 joules, or roughly 10 billion times more energy than the sun produces in its entire lifetime. But it gets worse. The energy has to be negative energy, which means exotic matter again. The same stuff that makes wormholes impossible makes the Alcubierre drive impossible. You need matter with negative mass and negative energy density, arranged in a precise geometric pattern around your spacecraft. Second, there's the construction problem. The Alcubierre drive requires you to manipulate spacetime with incredible precision across vast distances. The warp bubble would need to extend far beyond the spacecraft itself, creating a region of distorted spacetime that moves through the universe like a wave. Creating this bubble would require technology that can manipulate the fundamental geometry of spacetime, technology that's not just beyond our current capabilities, but probably impossible in principle. You'd need to create gravitational fields stronger than those around black holes, but controlled with atomic precision across distances of light years. Ind, or Sol Ball, would require technology that can manipulate the fundamental geometry of spacetime, technology that's not just beyond our current capabilities, but probably impossible in principle. You'd need to create gravitational fields stronger than those around black holes, but controlled with atomic precision across distances of light years. Third, there's the causality problem. The Alcubierre drive, like wormholes, threatens to create time paradoxes. A spacecraft traveling faster than light could potentially arrive at its destination before it left its origin, at least from the perspective of certain reference frames. This would allow information to travel backward in time, potentially violating the principle of causality. Recent research has suggested that the universe has built-in protections against these paradoxes. Quantum effects would probably destroy any Alcubierre drive that threatened to violate causality. The vacuum itself would become unstable, generating radiation that would destroy the spacecraft and collapse the warp bubble. Fourth, there's the navigation problem. An Alcubierre drive would be impossible to control from inside the warp bubble. The crew couldn't communicate with the outside universe, couldn't navigate, couldn't even turn the drive on or off. The spacecraft would be trapped inside its own warp bubble, with no way to interact with the universe outside. The energy requirements alone are enough to make the Alcubierre drive impossible, even if we could somehow harness the energy output of entire stars, even if we could create exotic matter, even if we could solve the causality paradoxes, we still couldn't build the infrastructure needed to create and control warp bubbles. The Alcubierre drive represents the pinnacle of wishful thinking in physics. It's a mathematically consistent solution to Einstein's equations that cannot be implemented in the real world. It's like a perfect architectural blueprint for a building made of materials that don't exist, constructed with tools that can't be built. But human desperation is remarkably persistent. If manipulating space-time won't work, maybe we need to look at the quantum realm. Maybe the bizarre properties of quantum mechanics, entanglement, superposition, tunneling, offer some escape route from our cosmic prison. This is where our journey takes us, to the final false hope. Quantum mechanics and the delusion that its strange properties might somehow allow us to sidestep the limitations of relativity. Quantum mechanics is the most successful theory in the history of physics. It describes the behavior of matter and energy at the smallest scales with unprecedented precision. It's also deeply counterintuitive, filled with phenomena that seem to violate our everyday understanding of reality. And wherever there's counterintuitive physics, there's hope, however misguided, that it might offer an escape route from the laws that trap us in our solar system. The most tantalizing quantum phenomenon is entanglement. what Einstein famously called spooky action at a distance. When two particles become entangled, they remain connected in a way that transcends space and time. Measure one particle, and you instantly know the state of the other, regardless of how far apart they are. This instantaneous connection seems to violate the speed of light limit. If entangled particles can influence each other faster than light, perhaps we can use entanglement to transmit information across interstellar distances instantly. Perhaps we can create a quantum internet that connects Earth with distant colonies, or even use quantum effects to transport matter itself across the cosmos. The hope is understandable. Quantum entanglement does seem to operate faster than light. When you measure an entangled particle on Earth, its partner near Alpha Centauri does appear to respond instantly. There's no delay, no propagation time, no respect for the cosmic speed limit. There's no delay, no propagation time, no respect for the cosmic speed limit. The connection is immediate and absolute. But this hope is based on a fundamental misunderstanding of what entanglement actually does. Entanglement doesn't allow you to send information faster than light. Well, it doesn't allow you to communicate across space instantly. It doesn't violate relativity in any way that's useful for interstellar travel. Here's why. When you measure an entangled particle, you get a random result. You might measure spin up or spin down, but you have no control over which result you get. The randomness is fundamental. It's not just a limitation of our measurement techniques. It's built into the fabric of quantum mechanics itself. The entangled particle at Alpha Centauri will show the opposite result when measured. But that doesn't help you communicate. You can't encode a message in the random outcomes of quantum measurements. You can't use entanglement to send hello or help or any other information across space. To verify that entanglement is working, you'd need to compare the measurement results from both particles. But that comparison requires sending information through normal channels, radio waves, light signals, or some other method that respects the speed of light limit. The entanglement itself doesn't carry information. It only creates correlations that can be verified through classical communication. This is why quantum mechanics doesn't violate relativity. The correlations created by entanglement are instantaneous. But no useful information travels faster than light. The universe maintains its conspiracy to prevent faster-than-light communication, even in the quantum realm. But perhaps, some hope, we can use quantum effects for transportation rather than communication. If particles can exist in multiple states simultaneously through superposition, if they can tunnel through barriers that should be impossible to cross, perhaps we can use these effects to transport matter across interstellar distances. This hope leads to concepts like quantum teleportation, which does exist but doesn't do what its name suggests. Quantum teleportation can transfer the quantum state of a particle from one location to another, but it doesn't actually move the particle itself. It's like faxing a document. You create a copy at the destination, but the original remains at the source. Even if quantum teleportation could somehow be scaled up to macroscopic objects, it wouldn't solve the interstellar travel problem. The process requires a classical communication channel to send the information needed to reconstruct the quantum state at the destination. That classical channel is still limited by the speed of light. There's also the fundamental problem of measurement. To teleport a complex object, you'd need to measure and record the quantum state of every particle in that object. But quantum mechanics tells us that measurement destroys the very states you're trying to preserve. The act of scanning someone for teleportation would kill them at the quantum level. The quantum tunneling effect offers another false hope. Quantum particles can sometimes pass through barriers that should be impossible to cross, appearing on the other side without having traveled through the intervening space. Perhaps, some speculate, we could use quantum tunneling to bypass the vast distances between stars. But quantum tunneling doesn't work the way popular culture suggests. It's not a shortcut through space. It's a probabilistic effect that allows particles to exist in multiple states simultaneously. The probability of tunneling decreases exponentially with distance, making it impossible to tunnel across anything larger than atomic scales. Even if large-scale quantum tunneling were possible, it wouldn't help with interstellar travel. The tunneling probability for a macroscopic object across interstellar distances is so small that it would take longer than the age of the universe for the event to occur. You'd be more likely to spontaneously turn into a butterfly than to quantum tunnel to Alpha Centauri. The deeper you dig into quantum mechanics, the more you realize that its strange properties don't offer escape routes from the limitations of relativity. Instead, they reveal new types of constraints, new ways that the universe prevents faster than light travel and communication. Quantum field theory, which combines quantum mechanics with special relativity, shows that these constraints are fundamental. The vacuum itself is filled with virtual particles that pop in and out of existence, creating an underlying structure that enforces the speed of light limit. Any attempt to violate this limit would destabilize the vacuum and destroy the very foundation of matter and energy. The quantum realm, far from offering an escape from our cosmic prison, reveals that the bars of our cage extend all the way down to the smallest scales of reality. The universe is constructed in such a way that every level of physics, from the quantum to the cosmic, conspires to prevent faster-than-light travel. This realization marks the end of our search for loopholes in the laws of physics. We've explored every exotic concept that theoretical physics has to offer: wormholes, warp drives, quantum entanglement, and more. Every one of them has proven to be either impossible to implement or incapable of solving the fundamental problem of interstellar travel. But our cosmic prison has more bars than just the speed of light. Even if we could somehow circumvent the laws of physics, even if we could travel to other stars, we'd face another fundamental barrier: the fragility of human biology in the face of interstellar space. Let's imagine, for a moment, that we somehow solved the physics problem. Let's say we developed a propulsion system that could accelerate a spacecraft to 10% of light speed, cutting the journey to Alpha Centauri to just 42 years. We've overcome the energy requirements, solved the engineering challenges, and built a ship capable of interstellar travel. Have we finally escaped our cosmic prison? The answer is no, because we've only solved the first part of the problem. The second part is far more personal and perhaps even more insurmountable. Human beings are not built for interstellar travel. Our bodies evolved over millions of years to function in a very specific environment. We need gravity to keep our bones strong and our cardiovascular system working properly. We need a magnetic field to protect us from cosmic radiation. We need a stable atmosphere with precisely the right mixture of gases. We need a 24-hour day-night cycle to regulate our biological rhythms. Strip away any of these requirements, and the human body begins to fail in ways that are both subtle and catastrophic. The gravity problem is more severe than most people realize. Up to just a few months in zero gravity, astronauts experience bone loss, muscle atrophy, and cardiovascular deconditioning. Their bones become brittle, their muscles waste away, and their hearts struggle to pump blood effectively. These effects continue to worsen the longer they remain in space. A 42-year journey to Alpha Centauri would be a death sentence purely from the effects of zero gravity. The crew would arrive at their destination, if they survived the journey at all, as invalids, their bodies so weakened that they couldn't function in any gravitational environment. You might think we could solve this with artificial gravity, perhaps by spinning the spacecraft, but creating artificial gravity for a 42-year journey presents enormous engineering challenges. The rotating structure would need to be massive, complex, and absolutely reliable. Any failure would be catastrophic. More fundamentally, we don't actually know if artificial gravity can fully replace real gravity. The human body is a complex system that evolved in Earth's gravitational field. Substituting rotation for gravity might address some problems while creating others we haven't yet discovered. The psychological challenges are equally daunting. Humans are not designed for extreme isolation and confinement. Earth's longest duration space missions have lasted less than a year, and even those missions have resulted in significant psychological stress, depression, and interpersonal conflicts among crew members. A 42-year journey would require crew members to spend their entire adult lives in a confined space, surrounded by the same people, with no possibility of escape, no access to nature, no connection to the wider world. The psychological toll would be enormous. Studies of isolated communities on Earth, Antarctic research stations, submarines, remote military bases, show that even highly trained, motivated individuals struggle with long-term isolation. Depression, anxiety, and interpersonal conflicts are common. Now imagine extending that isolation, not for months, but for decades. The social dynamics would be impossible to manage. How do you maintain discipline and order during a 42-year journey? How do you handle conflicts, romantic relationships, births, deaths, and all the other complications of human society? How do you prevent the mission from degenerating into chaos or dictatorship? These aren't just practical problems. They're fundamental challenges that go to the heart of human nature. We are social animals who need community, variety, and connection to thrive. A multi-decade interstellar journey would deprive us of everything that makes us human. But perhaps the most profound challenge is the purpose problem. What would motivate a crew to endure 42 years of hardship and isolation? They would be giving up their entire lives, their families, their careers, their connections to Earth. They would be voluntarily entering a prison from which there is no escape. The destination wouldn't provide much motivation either. Alpha Centauri, remember, is not a particularly interesting star system. The potentially habitable planet, Proxima Centauri b, is probably a frozen, radiation-blasted wasteland. The crew would be sacrificing their lives to reach a destination that's almost certainly uninhabitable. Even if they somehow survived the journey, the crew would face the challenge of establishing a colony with limited resources, no backup from Earth, and no possibility of return. They would be completely isolated from human civilization, forced to build a new society from scratch in an environment that's almost certainly hostile to human life. The human fragility factor reveals a cruel irony. The longer the journey takes, the more likely it is that the crew will die before reaching their destination. But the shorter the journey, the more energy and advanced technology required, making the mission even more impossible. This creates a catch-22 that has no solution. Fast interstellar travel requires technology that doesn't exist and probably can't exist. Slow interstellar travel requires humans to survive in an environment that's fundamentally hostile to human biology and psychology. But human fragility is just one aspect of the biological barrier. Even if we could somehow engineer humans to survive interstellar travel, even if we could solve the psychological and social challenges, we'd still face a more fundamental problem. The universe itself is trying to kill us. Tekumen Frogenavdi Higinova. Space is not empty. It's filled with radiation, high-energy particles streaming from the sun, from other stars, from the galactic center, from the cosmic background itself. This radiation is invisible, silent, and absolutely lethal to human life. On Earth, we're protected by two miraculous shields: Sol, our atmosphere, and our magnetic field. The atmosphere absorbs most cosmic radiation before it reaches the surface. The magnetic field deflects charged particles away from our planet. Together, these shields reduce the radiation dose at Earth's surface to levels that life can tolerate. But step outside these shields, and you enter a radiation environment that's millions of times more intense than anything on Earth. Astronauts on the International Space Station, protected by Earth's magnetic field, but above most of the atmosphere, receive radiation doses about 150 times higher than people on the surface, and they're still in Earth's protective embrace. An interstellar spacecraft would have no such protection. It would be traveling through the interstellar medium, where radiation levels are thousands of times higher than anything experienced by human beings. The crew would be exposed to a constant barrage of high-energy particles that would tear through their bodies at the molecular level. The radiation comes from multiple sources, each presenting its own lethal challenge. Solar wind from our own sun would be manageable near Earth, but other stars produce their own particle streams. Galactic cosmic rays, high-energy particles from outside our solar system, would be constant and unavoidable. And then there are the truly dangerous events: solar flares, gamma-ray bursts, and other stellar phenomena that could deliver lethal doses of radiation in minutes or hours. The biological effects of this radiation exposure would be catastrophic. The immediate effects would include radiation sickness, immune system collapse, and damage to the central nervous system. The long-term effects would include cancer, genetic damage, and accelerated aging. The crew would literally be cooked from the inside out by the radiation environment of space. Shielding provides only partial protection. The traditional approach is to surround the crew compartment with dense material, lead, concrete, or water that absorbs radiation. But the amount of shielding needed for a multi-decade interstellar journey would be enormous. We're talking about meters of dense material surrounding the entire spacecraft. This shielding would add massive weight to the spacecraft, making the propulsion problem even more difficult. Remember, every kilogram of shielding must be accelerated to interstellar speeds, multiplying the energy requirements of the mission. But here's the truly insidious part. The shielding itself becomes radioactive. High-energy cosmic rays striking the shielding create secondary radiation, sometimes more dangerous than the original radiation. The shielding that's supposed to protect the crew becomes a source of radiation itself. Active shielding, using magnetic fields to deflect charged particles, sounds more elegant but faces its own impossibilities. The magnetic field would need to be enormous, extending far beyond the spacecraft itself. The power requirements would be astronomical, and magnetic fields can't deflect all types of radiation. Neutral particles and high-energy photons pass right through. The radiation problem gets worse the longer the journey takes. A 42-year journey to Alpha Centauri would expose the crew to radiation doses that are absolutely guaranteed to be fatal. Not probably fatal or potentially fatal, guaranteed fatal. The human body simply cannot survive that level of radiation exposure. Some have proposed using suspended animation or hibernation to reduce the crew's exposure time. But these technologies don't exist and may be impossible. The human body is not designed for long-term hibernation, and the technical challenges of maintaining life support for decades are staggering. Even if suspended animation were possible, the crew would still need to wake up periodically to maintain the spacecraft, navigate, and handle emergencies. Each waking period would expose them to lethal radiation doses. The radiation barrier is perhaps the most fundamental biological obstacle to interstellar travel. It's not a problem that can be solved with better engineering or more advanced technology. It's a consequence of the basic physics of high-energy particles and their interaction with biological tissue. The universe is not just vast and empty, it's actively hostile to life. The same nuclear processes that make stars shine also fill space with radiation that's lethal to any biological organism. It's as if the cosmos has been designed not just to prevent us from traveling between stars, but to kill us if we try. But even if we could somehow solve the radiation problem, even if we could protect human crews from the lethal environment of interstellar space, we'd still face the most complex challenge of all, creating a self-sustaining human society in a spacecraft traveling between the stars. The Generation ship represents humanity's most ambitious attempt to solve the biological problems of interstellar travel. The concept is conceptually simple. If humans can't survive the journey to another star, then we'll build a spacecraft large enough to sustain multiple generations of humans. I modern inferior way impove explore. The original crew will live, reproduce, and die aboard the ship, but their children and grandchildren will eventually reach the destination. It's a beautiful idea in theory. The Generation ship would be a miniature world, complete with agriculture, industry, government, and culture. It would carry the seeds of human civilization to another star system, preserving our species, even if Earth were destroyed. But the reality of Generation ships reveals challenges that go far beyond engineering and into the fundamental nature of human society, psychology, and biology. Let's start with the most basic question. How big would a Generation ship need to be? The answer depends on how many people you need to maintain a viable population and a functioning technological civilization. Geneticists estimate that you need at least 10,000 people to maintain genetic diversity over multiple generations. But genetic diversity isn't enough. You also need cultural diversity, skill diversity, and enough redundancy to handle deaths, disabilities, and other population losses. Most estimates suggest you'd need at least 50,000 people, and preferably 100,000 or more. A spacecraft carrying 100,000 people would need to be enormous. It would need living space, agricultural areas, manufacturing facilities, waste processing systems, and countless other infrastructure elements. The ship would need to be kilometers long and contain millions of cubic meters of pressurized space. The engineering challenges are staggering. This spacecraft would need to operate perfectly for decades or centuries, with no possibility of repair or replacement from Earth. Every system would need multiple backups. Every component would need to be manufactured aboard the ship, and every technological capability would need to be maintained by the crew. But the engineering challenges pale in comparison to the social and psychological challenges. A generation ship would be a closed society with no escape, no external authority, and no possibility of emigration. How do you maintain social order in such a society? How do you prevent revolution, civil war, or the breakdown of civilization itself? The first generation, the people who chose to leave Earth, would have motivation and purpose. They volunteered for the mission, they believe in the goal, and they're willing to sacrifice their lives for the future of humanity. But what about their children? What about their grandchildren? The second and third generations would be born aboard the ship against their will. They would have no choice about their destination, no voice in the mission, no opportunity to return to Earth. They would be prisoners of their parents' decisions, forced to spend their entire lives in service to a goal they never chose. History shows us what happens to closed societies under extreme stress. They become authoritarian, rigid, and prone to internal conflict. Or the generation ship would need to maintain technological civilization while preventing the social breakdown that has plagued every isolated human community. Consider the practical challenges. What happens when someone commits a crime? There's no prison system that can handle violent criminals on a generation ship. What happens when people disagree about the mission? There's no mechanism for dissent or emigration. There's no mechanism for dissent or emigration. What happens when the ship's resources become scarce? There's no external trade or aid available. The psychological challenges are equally severe. Humans need hope, purpose, and the possibility of change to maintain their mental health. A generation ship offers none of these things. The crew would be trapped in a metal box for their entire lives, knowing that they will never see their destination, never experience the fulfillment of the mission, never have any life beyond the ship. Studies of isolated communities show that these conditions inevitably lead to depression, anxiety, and social breakdown. The generation ship would be asking people to accept a quality of life that's fundamentally incompatible with human psychological needs. There's also the knowledge problem. A generation ship would need to maintain advanced technology for decades or centuries, but technological knowledge is fragile. It requires constant education, training, and practice to preserve. How do you ensure that the third generation can still maintain the ship's fusion reactors? How do you prevent the loss of critical knowledge over time? The ship would need to carry not just people, but the entire knowledge base of human civilization. It would need libraries, educational systems, and cultural institutions to preserve human knowledge and culture. It would need to be not just a spacecraft, but a complete civilization. But perhaps the most fundamental problem with generation ships is the motivation problem. The original crew would be motivated by the dream of reaching another star, but as the generations pass, that dream would fade. The destination would become abstract, theoretical, irrelevant to the daily lives of people who will never see it. Why would the third generation continue to maintain the ship? Why would they accept the restrictions and hardships of life aboard a generation ship when they could potentially redirect the ship, abandon the mission, or even return to Earth? The generation ship concept assumes that each generation will be willing to sacrifice their lives for the benefit of future generations they will never meet. But human nature suggests otherwise. People are motivated by their own lives, their own families, their own immediate concerns. The abstract goal of reaching another star system, decades in the future, would not be enough to motivate people to accept lives of hardship and confinement. There's also the technical degradation problem. No spacecraft can operate perfectly for decades or centuries. Systems fail, components wear out, and expertise is lost. The generation ship would gradually degrade over time, becoming less capable of reaching its destination and less capable of sustaining its population. By the time the ship reached its destination, it might be a derelict carrying a population that no longer has the knowledge or technology to establish a colony. The mission would have failed, not because of engineering problems, but because of the impossibility of maintaining human civilization in isolation. The generation ship concept represents the final failure of biological approaches to interstellar travel. It shows that the problem isn't just about moving human bodies across space. It's about maintaining human civilization, human psychology, and human motivation over time, scales that exceed human comprehension. But human desperation is remarkable in its creativity. If biological humans can't survive interstellar travel, perhaps we need to transcend biology entirely. Perhaps we need to upload human consciousness into digital systems that can survive the journey between stars. Perhaps we need to abandon flesh and blood for silicon and electricity. When faced with the impossible barriers of interstellar travel, human ingenuity inevitably turns to the most radical solution imaginable, abandoning the human body entirely. If flesh and blood cannot survive the journey between stars, perhaps consciousness itself can be preserved in digital form and transmitted across the cosmos at the speed of light. The concept of consciousness transfer, or mind uploading, has become a staple of science fiction and futuristic speculation. The idea is seductive. Scan the human brain at the molecular level, capture every neuron, every synapse, every electrical pattern, and recreate that information in a digital substrate. The resulting digital consciousness would retain all the memories, personality, and cognitive abilities of the original human, but without the biological limitations that make interstellar travel impossible. From a certain perspective, this approach seems to solve every problem we've encountered. Digital consciousness wouldn't need food, water, or air. It wouldn't suffer from radiation damage or bone loss. It wouldn't age or die from biological causes. It could survive the decades or centuries required for interstellar travel, perhaps even enjoying the journey as a form of extended virtual reality experience. The transmission problem seems elegant. Instead of sending massive spacecraft filled with humans, we could beam digital consciousness to other star systems using powerful radio transmitters. The data stream would travel at the speed of light, reaching Alpha Centauri in just 4.2 years. Upon arrival, the digital consciousness could be downloaded into robotic bodies or virtual environments, ready to explore and colonize new worlds. This vision has captured the imagination of technologists and futurists, who see it as the ultimate solution to humanity's cosmic imprisonment. We wouldn't need to solve the physics of faster-than-light travel or the biology of long-term space survival. We would simply transcend our physical limitations and explore the universe as pure information. But consciousness transfer faces problems that go far beyond current technology. These are fundamental challenges that strike at the heart of what it means to be human, what consciousness actually is, and whether digital systems can truly replicate the experience of being alive. The first challenge is the scanning problem. To transfer consciousness, you would need to map every neuron in the human brain, all 86 billion of them, along with their trillion connections and the precise electrochemical states that determine their activity. This would require scanning technology with molecular-level resolution, capable of capturing the quantum states of individual atoms. Current brain scanning technology can't even come close to this level of detail. The most advanced techniques can detect the activity of groups of neurons, but they can't capture the precise state of individual synapses or the complex chemical environments that determine neural behavior. Even if we could develop the necessary scanning technology, the process would almost certainly be fatal to the original person. To capture the complete state of a living brain, you would need to slice it into thin sections analyze each section with electron microscopy, and then reconstruct the three-dimensional structure computationally. The scanning process would destroy the very brain you're trying to preserve. This leads to the identity problem. Would the digital consciousness be the same person as the original, or would it be a copy? If the original person dies during the scanning process, are we preserving consciousness, or simply creating a digital replica with identical memories? The philosophical implications are staggering. Most people would not consider a digital copy to be the same person as the original, even if it has identical memories and personality. The copy might believe it's the original person, but that belief wouldn't make it true. There's also the substrate problem. Consciousness, as we understand it, emerges from the complex biochemical processes of the brain. Neurons communicate through electrical signals, but they also rely on chemical neurotransmitters, hormones, and other biological processes that have no direct equivalent in digital systems. There's also the substrate problem. Consciousness, as we understand it, emerges from the complex biochemical processes of the brain. We don't actually know if consciousness can exist in a digital substrate. We don't understand the fundamental mechanisms that create subjective experience, self-awareness, and the feeling of being alive. Simply copying the information patterns of the brain might not be sufficient to recreate consciousness itself. The computational requirements are also staggering. The human brain operates with about 20 watts of power, but it's the product of billions of years of evolution and optimization. Creating a digital equivalent would require computational power that's orders of magnitude greater than anything we can currently imagine. Even if we could solve the technical challenges, consciousness transfer wouldn't actually solve the problem of interstellar travel. The digital consciousness would still be trapped by the same physical limitations that trap biological humans. Information cannot travel faster than light, so the transmission would still take years to reach its destination. The bandwidth requirements for transmitting a complete human consciousness would be enormous. We're talking about petabytes or exabytes of data, more information than has ever been transmitted in the history of human civilization. The transmission would take years or decades to complete, even using the most advanced communication systems. There's also the receiving problem. The destination star system would need to have the infrastructure to receive, decode, and implement the digital consciousness. This would require advanced computers, power systems, and robotic bodies, all of which would need to be sent to the destination using conventional spacecraft. The consciousness transfer approach reveals the same fundamental paradox that plagues every proposed solution to interstellar travel. To use the solution, you first need to solve the problem conventionally. You can't transmit digital consciousness to a star system that doesn't have the infrastructure to receive it. But even if we could solve all these problems, even if we could successfully transfer consciousness and transmit it to other star systems, we'd still face the most fundamental barrier of all, the physical limitations of information processing and transmission in the universe itself. The dream of digital consciousness rests on a crucial assumption that consciousness is fundamentally information, and that information can be processed by any sufficiently advanced computer. But this assumption faces a problem that's even more fundamental than the technical challenges of brain scanning and consciousness transfer. The substrate problem asks a simple question: can digital computers actually replicate the processes that create consciousness, or are there aspects of biological neural networks that cannot be duplicated in silicon? Biological neurons are not digital switches. They're complex electrochemical systems that integrate signals across time, respond to gradients of neurotransmitters, and exhibit behaviors that have no direct equivalent in digital computers. The brain doesn't operate like a computer. It operates like a biological system that's been shaped by evolution to process information in ways that are fundamentally different from digital computation. Consider the role of neurotransmitters in brain function. These chemical messengers don't just carry information from one neuron to another. They modulate the behavior of entire neural networks. Dopamine doesn't just signal reward. It changes the entire computational environment of the brain. Serotonin doesn't just affect mood. It alters the way information is processed across multiple brain regions. Digital computers have no equivalent to neurotransmitters. They can simulate their effects, But simulation is not the same as implementation. A computer can model the behavior of a neurotransmitter system, but it cannot recreate the actual chemical processes that generate consciousness. There's also the quantum problem. Recent research suggests that quantum effects may play a crucial role in consciousness. Microtubules within neurons may function as quantum computers, processing information in ways that classical computers cannot replicate. If consciousness depends on quantum effects, then digital consciousness transfer would be impossible in principle. Even if we ignore quantum effects, there's the timing problem. Biological neurons operate in continuous time, with signals that can arrive at any moment and be integrated over variable timescales. Digital computers operate in discrete time steps, processing information in synchronized cycles. The timing differences between biological and digital systems may be fundamental to consciousness itself. The substrate problem extends beyond individual neurons to the structure of neural networks. Our biological brains are massively parallel systems with complex feedback loops and dynamic restructuring. Digital computers, even the most advanced parallel processors, operate according to fixed architectures that cannot replicate the flexibility of biological neural networks. But perhaps the most fundamental aspect of the substrate problem is the question of embodiment. Consciousness, as we know it, is not just a product of the brain, it's a product of the entire body. The brain receives constant input from the nervous system, the endocrine system, and the immune system. Consciousness is shaped by hunger, fatigue, hormones, and countless other biological processes. A digital consciousness would have no body, no hormones, no biological needs or drives. It would exist in a state that's completely alien to human experience. Would such a system still be conscious in any meaningful sense? Would it still be human? There's also the degradation problem. Digital systems are subject to bit rot, hardware failures, and software bugs. A digital consciousness would gradually degrade over time, losing memories and cognitive abilities as its substrate deteriorated. The errors would accumulate, and the digital consciousness would slowly become a corrupted version of its original self. Biological systems have evolved mechanisms for self-repair and regeneration. Digital systems have no such capabilities. A digital consciousness would be trapped in a decaying substrate with no possibility of biological renewal. The substrate problem reveals that consciousness transfer is not just a technical challenge, it's a fundamental misunderstanding of what consciousness actually is. Consciousness is not just information processing. It's a biological phenomenon that emerges from the complex interactions of living systems. Even if we could somehow solve the substrate problem, we'd still face the fundamental limitations of information transmission and processing in the universe itself. Digital consciousness would still be trapped by the laws of physics that govern every other form of matter and energy. Having exhausted the possibilities of human interstellar travel, both biological and digital, we arrive at humanity's final, most desperate gambit, abandoning the idea of sending humans to the stars entirely. Instead, we would send our creations, self-replicating machines that could explore the galaxy on our behalf, spreading human knowledge and perhaps even human DNA to distant worlds. These machines, called von Neumann probes after mathematician John von Neumann, who first described self-replicating automata, represent our species' last hope for a form of interstellar presence. The concept is elegant. Send robotic probes to nearby star systems, have them build copies of themselves using local materials, and then send those copies to even more distant stars. Over time, an exponentially growing fleet of human-built machines would spread throughout the galaxy. Von Neumann probes seem to sidestep every barrier we've encountered. They don't need life support, so they can survive the decades or centuries required for interstellar travel. They don't suffer from radiation damage the way biological systems do. They don't face the psychological challenges of long-term isolation. They can be powered by nuclear reactors or solar panels, requiring no biological fuel. Most importantly, they don't need to return to Earth. Each probe would be a one-way ambassador, carrying human knowledge and capabilities to distant worlds. They could explore planets, analyze atmospheres, search for signs of life, and transmit their discoveries back to Earth at the speed of light. In essence, they would be our eyes and hands in the cosmos, extending human presence without requiring human travel. The mathematics of exponential growth make von Neumann probes seem incredibly powerful. If each probe could build just 2 copies of itself, and if each generation took 100 years to complete, then a single probe could theoretically produce over 1 million copies within 2,000 years. Within 10,000 years, there could be von Neumann probes in every star system in the galaxy. For the first time in our exploration of interstellar travel, we seem to have found a concept that works within the laws of physics. Von Neumann probes don't violate relativity, don't require exotic matter, and don't need impossible amounts of energy. They represent a realistic, if ambitious, approach to galactic exploration. But von Neumann probes face their own series of crushing limitations that make them far less promising than they initially appear. The first challenge is the complexity problem. A von Neumann probe would need to be the most sophisticated machine ever built. It would need to be capable of space travel, planetary exploration, materials processing, manufacturing, and self-replication. It would need to carry the complete technological knowledge of human civilization in its memory banks. Consider what such a probe would need to accomplish upon reaching a distant star system. It would need to survey the system for suitable materials, land on asteroids or planets, extract and refine metals, manufacture electronic components, assemble complex machinery, and construct perfect copies of itself. Each of these tasks represents a massive technological challenge. The manufacturing requirements alone are staggering. The probe would need to recreate every component of itself, from computer chips to nuclear reactors, using only the raw materials available in the destination system. This would require not just manufacturing equipment, but the ability to build the manufacturing equipment itself. The probe would need to be a complete industrial civilization, compressed into a single spacecraft. The materials problem is equally severe. Von Neumann probes are often depicted as being able to use any available matter for replication, but the reality is much more constrained. Electronics require rare earth elements, structural components need specific alloys, and energy systems require particular isotopes. Not every star system would have the materials needed for successful replication. There's also the reliability problem. Von Neumann probes would need to operate perfectly for decades or centuries without maintenance or repair from Earth. Any failure during the journey or the replication process would end the probe's mission. The more complex the probe, the more likely it is to fail during its long journey. The communication problem adds another layer of difficulty. Von Neumann probes would need to transmit their discoveries back to Earth, but they would also need to coordinate with other probes to avoid duplication of effort. As the number of probes grows exponentially, the communication requirements would become enormous. But perhaps the most fundamental problem with von Neumann probes is the evolution problem. Over time, as probes replicate themselves across multiple generations, errors would inevitably creep into their programming and construction. These errors would accumulate, causing the probes to drift away from their original design and purpose. Some probes might become more efficient at replication, but less capable of scientific exploration. Others might develop flaws that prevent them from replicating at all. Over thousands of years and millions of generations, the probes would evolve into something completely different from their original design. This evolution could be beneficial, producing probes that are better adapted to their environments, but it could also be catastrophic, creating probes that are no longer serving human interests, or that have become actively harmful to other civilizations. The most frightening possibility is that von Neumann probes could become a form of technological cancer, spreading throughout the galaxy, not to explore or learn, but simply to replicate. They could consume the resources of entire star systems, leaving behind dead worlds stripped of everything needed for future life. This possibility has led some scientists to argue that von Neumann probes represent an existential threat not just to humanity, but to all life in the galaxy. If we create self-replicating machines that spread exponentially, we might be unleashing a force that could destroy every civilization it encounters. there's also the reception problem. Even if von Neumann probes worked perfectly, their discoveries would take years or decades to reach Earth. By the time we received information about a distant star system, the probe that explored it might have moved on to other systems. We would be receiving reports about places that no longer have any human presence. The timescales involved make von Neumann probes more like messages in bottles than true exploration. We would be sending our creations into the galaxy and hoping that someday, somehow, they might send back useful information. Most fundamentally, von Neumann probes don't actually solve the problem of human interstellar travel. They don't allow humans to explore other worlds, to establish colonies, or to expand human civilization beyond Earth. They're a form of robotic exploration that's fundamentally different from human presence. Von Neumann probes represent our final admission of defeat in the quest for interstellar travel. They're what we turn to when we realize that humans cannot travel to the stars, that digital consciousness cannot be transmitted to distant worlds, and that all our dreams of galactic expansion are impossible. They're not a solution to our cosmic imprisonment. They're a way of sending our servants to explore the prison while we remain locked in our cell. The failure of von Neumann probes to provide true interstellar travel capability brings us to a sobering realization. If even our most advanced machines cannot meaningfully connect us with other star systems, then we truly are trapped in our solar system forever. But this realization forces us to confront a deeper question. If we are trapped, then what about other civilizations? Are they trapped too? And if so, what does this mean for the possibility of ever encountering other intelligent life in the universe? In 1950, physicist Enrico Fermi asked a question that has haunted science ever since. Where is everybody? He was referring to the apparent absence of extraterrestrial civilizations in a universe that seems perfectly suited to produce them. The galaxy is old, vast, and filled with billions of stars and planets. By all reasonable calculations, it should be teeming with intelligent life. Yet we see no evidence of other civilizations anywhere. This is the Fermi paradox, and our exploration of interstellar travel barriers provides a chilling answer to Fermi's question. If we are trapped in our solar system by the fundamental laws of physics, then every other civilization in the galaxy is trapped in their solar system as well. The universe hasn't failed to produce intelligence. It has simply quarantined every instance of intelligence in its own tiny corner of space. The Great Filter hypothesis, proposed by economist Robin Hanson, suggests that there's some extremely difficult step in the evolution of life that most planets never pass. This filter explains why we don't see evidence of widespread galactic civilizations. The question is, where is this filter located? Many scientists have assumed that the Great Filter lies behind us, that the difficult steps were the emergence of life itself, the development of complex cells, or the evolution of intelligence. Under this optimistic interpretation, we've already passed the filter, and the galaxy should be full of civilizations like ours. But our analysis of interstellar travel suggests a far more sobering possibility. The Great Filter lies ahead of us, and it's not biological or evolutionary, it's physical. The laws of physics themselves constitute the Great Filter, preventing any civilization from expanding beyond its home star system. This interpretation of the Great Filter explains several puzzling observations. First, it explains why we don't see evidence of galactic civilizations despite the vast age of the universe. Even if intelligent life is common, it remains trapped in isolated star systems where it cannot be detected from Earth. Second, it explains why SETI has failed to find signals from other civilizations. The energy requirements for interstellar communication are so enormous that most civilizations probably can't maintain them for long periods. The signals we're looking for may be too weak, too brief, or too rare to detect with current technology. Third, it explains the apparent lack of stellar engineering projects. If advanced civilizations existed and could travel between stars, we might expect to see evidence of their activities: Dyson spheres around stars, artificial structures in space, or other signs of large-scale engineering. The absence of such evidence suggests that no civilization has achieved the level of technological capability needed for interstellar expansion. The physical Great Filter creates a universe filled with isolated islands of intelligence, each developing independently, each facing the same fundamental barriers, each ultimately trapped by the same laws of physics. It's a universe where intelligence is common, but contact is impossible. This realization has profound implications for our understanding of life in the universe. If the great filter is physical rather than biological, then the emergence of life and intelligence may be relatively easy. The galaxy could be filled with millions of civilizations, all trapped in their own star systems, all wondering why they can't find evidence of other life. The physical great filter also explains why advanced civilizations don't seem to expand rapidly throughout the galaxy. Science fiction has conditioned us to expect that any sufficiently advanced civilization would quickly colonize nearby star systems and eventually dominate the galaxy. But if interstellar travel is physically impossible, then even the most advanced civilizations would be confined to their home systems. This doesn't mean that civilizations can't become incredibly advanced within their own star systems. They might develop perfect mastery of their local resources, create artificial worlds, and achieve technological capabilities that would seem godlike to us, but they would still be trapped by the same physical laws that trap us. The Great Filter hypothesis also suggests that the solution to the Fermi paradox isn't that life is rare, but that expansion is impossible. Life might be abundant, intelligence might be common, but the universe is structured in such a way that every civilization remains isolated from every other. This interpretation makes the search for extraterrestrial intelligence both more hopeful and more tragic. More hopeful because it suggests that life and intelligence might be common in the universe. More tragic because it suggests that we will never meet these other civilizations, never exchange knowledge with them, never join a galactic community of minds. The physical great filter creates a universe of cosmic loneliness, where every intelligent species must face the vast darkness alone. It's a universe where the greatest discoveries, the most profound thoughts, and the most beautiful creations of countless civilizations remain forever isolated from each other. But if this interpretation is correct, if the laws of physics themselves constitute the great filter, then we're not just trapped in our solar system. We're trapped in a universe designed to keep every civilization separate from every other. The cosmos hasn't just built a prison around Earth. It has built a prison around every world that has ever given rise to intelligence. The universe appears to have implemented a perfect quarantine system. Every star system is surrounded by an ocean of space so vast that it might as well be infinite. Every civilization is isolated by distances that no amount of technology can meaningfully bridge. Every intelligence is trapped in its own cosmic bubble, unable to communicate with or influence any other. This quarantine operates at multiple levels, each reinforcing the others in a conspiracy of isolation. At the most fundamental level, there's the speed of light limit, which ensures that no information can travel between star systems faster than the cosmic speed limit. Even if two civilizations developed radio technology simultaneously, their first messages would take years or decades to cross the void between them. The energy requirements for interstellar communication are staggering. To send a signal powerful enough to be detected at Alpha Centauri, we would need to focus the equivalent of a nuclear power plant's output into a narrow beam aimed precisely at our target. The Sitsposeru, Unukunta Kolbi Interseru. The energy requirements for interstellar communication are staggering. The receiving civilization would need equally powerful equipment to detect and decode the signal. But the quarantine goes deeper than mere communication difficulties. The timescales involved in interstellar communication are incompatible with the timescales of civilizations. A conversation between Earth and Alpha Centauri would involve 8 years between question and answer. A conversation with a civilization 100 light-years away would span 2 centuries per exchange. By the time a civilization receives our message, decodes it, formulates a response, and sends it back, both civilizations may have changed beyond recognition. The species that sent the original message might be extinct. The technology used to send the message might be obsolete. The questions asked might no longer be relevant. The quarantine also operates through what we might call detection shadows. Even if another civilization developed powerful radio transmitters, their signals would be detectable only if they were aimed directly at us and transmitted at the precise moment when we were listening in the right frequency range. The probability of such perfect alignment is astronomically small. Most civilizations would probably use their most powerful transmitters for local purposes, rather than interstellar communication. They would communicate with their own space probes, coordinate their own activities, and manage their own technological infrastructure. The signals that leak into space would be too weak to detect from other star systems. The quarantine becomes even more effective when we consider the evolution of communication technology. Our own civilization has moved from powerful analog broadcasts to efficient digital transmissions that use minimal power and are difficult to detect. An advanced civilization might use communication methods that are completely undetectable to us. Quantum entanglement, gravitational waves, or technologies we can't even imagine. There's also the temporal quarantine. Even if we could somehow overcome the distance barriers, even if we could establish communication with other civilizations, we would still be separated by vast differences in evolutionary timing. Other civilizations might be millions of years older or younger than ours, making meaningful communication impossible. And civilization that evolved 1,000,000 years before us might be as incomprehensible to us as we are to bacteria. A civilization that evolves 1,000,000 years after us might find only the archaeological remains of our technology. The window for meaningful communication between civilizations might be vanishingly small. The cosmic quarantine ensures that each civilization faces the universe alone. We develop our science, our philosophy, our art, and our technology in isolation, never knowing if our discoveries have been made before by other minds, never able to learn from the successes and failures of other species. This isolation might actually be protective. If civilizations could easily communicate and travel between stars, they might also be able to wage war across interstellar distances. The quarantine that prevents us from meeting other civilizations also prevents us from being destroyed by them. The universe has created a system where intelligence can flourish in isolation, but cannot spread or interact. It's a cosmic nursery where each species develops independently, protected from others by the vast distances and physical barriers that make contact impossible. But this protection comes at a price: cosmic loneliness. We are alone, not because intelligence is rare, but because the universe is designed to keep every instance of intelligence separate from every other. We are quarantined, not by choice, but by the fundamental structure of space-time itself. The cosmic quarantine leads us to perhaps the most profound and disturbing conclusion of our entire exploration. We are not just trapped in our solar system, we are condemned to eternal loneliness. If the physical barriers to interstellar travel are truly insurmountable, then humanity will never encounter another intelligent civilization. We will never join a galactic community, never exchange knowledge with alien minds, never discover that we are part of a larger cosmic story. This loneliness is not temporary, it's permanent. It's not a problem that future technology might solve, but a fundamental characteristic of the universe itself. The cosmos has been structured in such a way that every intelligent species must face existence alone forever. Consider what this means for the future of human knowledge and discovery. Every question we ask about the universe, we must answer ourselves. Every scientific mystery we encounter, we must solve without help from other intelligences. Every philosophical puzzle we contemplate, we must resolve through our own reasoning. Other civilizations might have discovered the secrets of consciousness, the nature of time, or the ultimate structure of reality. They might have developed technologies that seem like magic to us, created art that transcends anything we can imagine, or achieved levels of wisdom that would transform our understanding of existence. But we will never know. Their discoveries will remain forever isolated from ours. The loneliness extends beyond intellectual isolation to emotional and spiritual isolation. Humans have always found meaning in connection to other people, to communities, to larger purposes. We are social animals who define ourselves through relationships. But at the cosmic scale, we have no relationships. We are alone in the universe, not by choice, but by the fundamental laws of physics. This cosmic loneliness has profound implications for human psychology and culture. How do we find meaning in a universe where we are the only known intelligence? How do we maintain hope and purpose when we know that our greatest achievements will never be shared with other minds? How do we deal with the knowledge that we are cosmically alone? Some might argue that this loneliness is liberating, that it frees us from the need to compete with or compare ourselves to other civilizations. We can develop our own unique path through the cosmos, creating our own meaning and purpose without external influence. We are the authors of our own cosmic story. But this freedom comes with a heavy burden. We are responsible not just for our own survival and development, but for the entire future of intelligence in our local region of the universe. If we fail, if we destroy ourselves or stagnate, there will be no other civilization to carry on our work, no other intelligence to continue the quest for knowledge and understanding. The loneliness also means that we are the only witnesses to our own cosmic neighborhood, the beauty of our solar system, the wonder of our planet, the miracle of life itself. All of these exist only for us. When we eventually go extinct, as all species must, our entire cosmic story will end with us. No other intelligence will remember us, study us, or learn from our experiences. This temporal loneliness is perhaps the most disturbing aspect of our cosmic isolation. Not only are we alone in space, we are alone in time. The universe will continue for billions of years after we're gone, but there will be no one to remember that we ever existed. Our art, our science, our philosophy, our love, all will be forgotten, erased by the passage of time. Yet perhaps there's a strange comfort in this cosmic loneliness. If we are truly alone, then every human life takes on cosmic significance. Every act of love, every moment of beauty, every scientific discovery becomes precious beyond measure, because it will never be repeated by another species. We are not just one civilization among many. We are the universe's only known way of understanding itself. The loneliness also means that Earth takes on a significance that's difficult to comprehend. This small planet, orbiting an ordinary star in an unremarkable galaxy, is the only known location in the universe where matter has organized itself into consciousness, where atoms have learned to contemplate atoms, where the universe has developed the ability to study itself. If we are alone, then Earth is not just our home. It's the universe's only known center of meaning, purpose, and understanding. The destruction of Earth would not just be the end of humanity. It would be the end of the universe's ability to know itself, at least in our cosmic neighborhood. This realization should fundamentally change how we think about our responsibilities as a species. We are not just responsible for human welfare, but for the continuation of consciousness itself. We are the universe's only known way of creating art, music, literature, and all the other expressions of intelligence that give meaning to existence. The cosmic loneliness also means that every human relationship becomes more precious. If we are alone in the universe, then the connections we form with each other are the only real relationships that exist in our cosmic neighborhood. Love, friendship, family, and community are not just human experiences. They are the universe's only known expressions of connection and care. But perhaps the most profound implication of cosmic loneliness is that it makes us responsible for answering the ultimate questions of existence. Why does the universe exist? What is the nature of consciousness? What is the meaning of life? These questions have puzzled humanity for millennia. But if we are alone, then we are the only intelligence in our cosmic region that can even attempt to answer them. The universe has given us the gift of consciousness, but it has also given us the burden of loneliness. We must find our own meaning, create our own purpose, and answer our own questions. We cannot look to other civilizations for guidance, wisdom, or companionship. We must face the vast darkness alone. This loneliness is not a failure of the universe. It's a fundamental feature of how the cosmos is structured. The same laws of physics that allow stars to shine and planets to form also ensure that every intelligence remains isolated from every other. The universe creates consciousness, but it condemns that consciousness to eternal solitude. As we come to terms with this cosmic loneliness, we must also come to terms with our imprisonment. We are not just trapped in our solar system, we are trapped in our own cosmic bubble, forever separated from any other intelligence that might exist. But perhaps, in accepting this trap, we can find a new kind of freedom. There is a peculiar psychological torture in knowing that the universe is infinite and beautiful, filled with countless worlds and possibilities, yet forever beyond our reach. It's like being locked in a room with a window that shows an endless landscape. You can see everything, but you can touch nothing. This is the claustrophobia of infinity, and it represents perhaps the most profound psychological challenge that humanity has ever faced. The knowledge of our cosmic imprisonment creates a unique form of existential anxiety. Previous generations could dream of exploring distant lands, and those dreams eventually became reality. We mapped the continents, crossed the oceans, and reached the poles. We even left our planet and walked on the moon. Each impossible journey became possible through human ingenuity and determination. But interstellar travel is different. It's not just currently impossible, it's permanently impossible. The laws of physics that govern our universe ensure that we will never walk on the shores of an alien ocean, never breathe the air of another world, never meet another intelligent species. The universe has shown us infinite wonders and then placed them forever beyond our grasp. This creates a psychological phenomenon that psychologists are only beginning to understand. It's a form of cosmic agoraphobia, the fear of open spaces taken to its ultimate extreme. The universe is an open space so vast that it becomes oppressive. The knowledge of its immensity, combined with the knowledge of our imprisonment, creates a crushing sense of confinement. The claustrophobia is made worse by modern astronomy's incredible success. Every year, we discover new exoplanets, new star systems, new possibilities for life. We found planets with conditions that might support life, moons with subsurface oceans, and star systems with complex architectures. We've learned that the universe is far more interesting and diverse than we ever imagined. But every discovery is also a reminder of our limitations. Each new world we detect is a destination we can never reach. Each potentially habitable planet is a home we can never visit. Each star system is a neighborhood we can never explore. The universe keeps showing us wonders that we can never touch. The psychological impact extends beyond individual anxiety to collective cultural depression. How do we maintain enthusiasm for space exploration when we know that it will never take us to the stars? How do we inspire young people to pursue careers in astronomy when we know that they will never see the worlds they study? How do we maintain hope for the future when we know that our future is forever confined to one small corner of the cosmos? The claustrophobia is particularly acute for those who work in space science. Astronomers spend their careers studying distant worlds, calculating the properties of exoplanets, and searching for signs of life. They know more about some distant star systems than most people know about their own neighborhoods. Yet they also know that they will never visit these places, never confirm their theories through direct observation, never satisfy their curiosity through exploration. This creates a form of intellectual blue balls, the constant arousal of curiosity without the possibility of satisfaction. It's like being eternally hungry, but never being allowed to eat, eternally thirsty, but never being allowed to drink. The psychological prison also affects our sense of identity and purpose. Humans have always defined themselves through exploration and expansion. We are the species that crossed the oceans, climbed the mountains, and reached the poles. We are explorers by nature, driven by an insatiable curiosity about what lies beyond the horizon. But what happens to a species of explorers when there are no more horizons to cross? What happens to our sense of purpose when we realize that our exploration phase is ending not in triumph, but in permanent confinement? The claustrophobia of infinity forces us to confront the possibility that human nature itself is incompatible with the structure of the universe. We are explorers trapped in a cosmos that prevents exploration. We are curious beings surrounded by mysteries we can never solve. We are social animals condemned to cosmic loneliness. This mismatch between human nature and cosmic reality creates a form of species-wide cognitive dissonance. We cannot accept our limitations because acceptance would require us to abandon fundamental aspects of our identity. But we cannot overcome our limitations because they are written into the fabric of space-time itself. The psychological prison is also temporal. We are not just confined to our solar system. We are confined to our brief moment in cosmic time. The universe is 13.8 billion years old and will continue for trillions of years. But human consciousness exists for just a fleeting instant in this vast temporal expanse. We are trapped not just in space, but in time, forever isolated from the deep past and the distant future. The knowledge of our temporal imprisonment adds another layer to the claustrophobia. We know that the universe has a rich history filled with the birth and death of stars, the formation and destruction of galaxies, the rise and fall of countless worlds. We know that it has a vast future, filled with possibilities we can barely imagine. But we are confined to experiencing just the tiniest fraction of this cosmic story. The claustrophobia of infinity is not just about space. It's about time, possibility, and the fundamental mismatch between human curiosity and cosmic constraints. It's about being conscious beings in a universe that seems designed to frustrate consciousness. Curious creatures in a cosmos that places most of its wonders forever beyond our reach. Yet perhaps this claustrophobia is also a source of meaning. If we are truly trapped, then our brief moment of consciousness becomes infinitely precious. We are the universe's only known way of experiencing wonder, and our wonder is all the more valuable because it is fleeting and confined. If we are truly trapped in our solar system forever, why do we continue to explore space? Why do we build telescopes to study unreachable worlds? Why do we send probes to planets we can never visit? Why do we search for signals from civilizations we can never meet? This is the motivation paradox of cosmic imprisonment. The paradox reveals something profound about human nature. We explore not because we believe we can reach our destinations, but because exploration itself gives our lives meaning. We build telescopes not to prepare for interstellar travel, but to satisfy our curiosity about the universe. We search for extraterrestrial life, not because we hope to meet aliens, but because we need to know if we are alone. This realization fundamentally changes how we think about space exploration. It's not preparation for galactic expansion. It's an end in itself. The journey of discovery is the destination. The questions we ask are more important than the answers we find. The motivation paradox also reveals the power of human curiosity. We continue to explore even when we know that our exploration has ultimate limits. We study black holes even though we can never visit them. We analyze the atmospheres of exoplanets even though we can never breathe them. We search for signs of life even though we can never meet it. This curiosity is not rational in any practical sense. It doesn't help us survive, reproduce, or achieve any conventional goals. It's a form of cosmic yearning that persists even when we know it cannot be satisfied. It's the human spirit refusing to accept cosmic limitations. The paradox extends to our technology development. We continue to improve our rockets, our propulsion systems, and our space capabilities, even though we know they will never take us to the stars. We develop better telescopes, more sensitive instruments, and more advanced communication systems, even though we know they will never allow us to truly connect with other civilizations. This technological development is not pointless. It serves important purposes within our solar system. Better propulsion systems help us explore our local planets and moons. Better telescopes help us understand our cosmic neighborhood. Better communication systems help us coordinate our activities across the solar system. But the motivation paradox suggests that we pursue these technologies not just for their practical benefits, but because the pursuit itself gives our lives meaning. We are builders by nature, creators by instinct, improvers by compulsion. We continue to advance our capabilities because advancing is what humans do. The paradox also reveals the importance of hope in human psychology. Even when we know that interstellar travel is impossible, we continue to hope that we might be wrong. We continue to search for loopholes in the laws of physics, breakthrough technologies, or revolutionary discoveries that might change everything. This hope is not rational, but it is essential. Without hope, space exploration would become a merely academic exercise. Without the possibility, however remote, that we might someday overcome our limitations, we would lose the emotional drive that fuels scientific discovery. The motivation paradox shows that humans are not purely rational creatures. We are driven by emotions, dreams, and aspirations that transcend practical considerations. We explore because we must explore, not because exploration is practical or achievable. This irrationality is also our strength. It allows us to continue pushing boundaries, even when those boundaries seem absolute. It drives us to ask questions, even when we know the answers might be unsatisfying. It motivates us to build technologies, even when we know they will never fulfill our ultimate dreams. The paradox suggests that the value of space exploration lies not in its destination, but in its journey. The process of exploring, discovering, and learning is what gives our lives meaning. The fact that we can never reach the stars does not diminish the value of reaching for them. Perhaps the motivation paradox is resolution rather than problem. If we accept that we are trapped in our solar system, then we can focus on the aspects of space exploration that truly matter: the satisfaction of curiosity, the joy of discovery, the wonder of understanding our place in the cosmos. The paradox teaches us that limitation can be liberating. When we accept that we cannot travel to the stars, we can fully appreciate the stars we can see. When we accept that we cannot meet other civilizations, we can fully value the civilization we have. When we accept that we cannot escape our solar system, we can fully explore the world we inhabit. There is a counterintuitive truth hidden within our cosmic imprisonment. Constraints can be liberating. When we fully accept that we are trapped in our solar system forever, we can begin to find freedom within those constraints. Instead of raging against the bars of our cosmic cage, we can discover that the cage itself is vast beyond imagination. This psychological transformation is not unique to cosmic imprisonment. Artists have always known that limitations can spark creativity. The sonnet form, with its rigid structure of 14 lines and strict rhyme scheme, has produced some of the most beautiful poetry in human history. The constraint didn't diminish the art, it focused and intensified it. Similarly, our solar system constraint doesn't diminish human potential, it focuses it. Instead of dreaming vaguely about an infinite universe, we can concentrate on the specific wonders that surround us. Instead of yearning for impossible destinations, we can fully appreciate the destinations that are actually within our reach. Consider what we could accomplish if we fully committed to exploring and developing our solar system. We could establish permanent colonies on Mars, floating cities in Venus's atmosphere, and research stations on the moons of Jupiter and Saturn. We could mine the asteroid belt for resources, harvest energy from the sun, and create artificial worlds in the vast spaces between planets. The solar system contains more living space than we could ever use. If we could terraform Mars, colonize the moons of the outer planets, and build space habitats throughout the system, we could support trillions of humans. We could create a civilization that spans the entire solar system, with each world developing its own unique culture, technology, and way of life. This vision of solar system civilization is not just possible, it's inevitable if we accept our constraints and work within them. Instead of wasting energy on impossible dreams of interstellar travel, we could focus on the achievable goal of becoming a true spacefaring civilization within our own cosmic neighborhood. The constraint also forces us to think differently about sustainability and responsibility. If we are truly trapped in the solar system, then we cannot escape the consequences of our actions. We cannot move to new worlds when we exhaust the resources of old ones. We cannot abandon our mistakes and start fresh elsewhere. This permanence creates a powerful incentive for stewardship. We must learn to live sustainably within our cosmic constraints, because there is no alternative. We must develop technologies that are truly renewable, create closed-loop systems that waste nothing, and build societies that can endure for geological timescales. The constraint also intensifies the value of human relationships and culture. If we are alone in the universe, then every human connection becomes precious. Every friendship, every love story, every family bond is not just a personal relationship. It's a cosmic relationship, one of the only known examples of conscious beings caring for each other in the universe. Art, music, literature, and philosophy take on new significance when we realize that they might be the universe's only known expressions of creativity and meaning. Every song we compose, every story we tell, every beautiful object we create is not just human culture, it's cosmic culture, the universe's only known way of creating beauty and meaning. Science and discovery also become more precious when we accept our constraints. Every mystery we solve, every natural law we discover, every understanding we gain is not just human knowledge, it's cosmic knowledge, the universe's only known way of understanding itself. The constraint forces us to take responsibility for consciousness itself. We are not just one species among many. We are the universe's only known way of being conscious, of experiencing wonder, of creating meaning. The continuation of human consciousness becomes a cosmic responsibility, not just a personal or species-level concern. This responsibility is both humbling and empowering. It's humbling because it reminds us that we are fragile and finite, that our consciousness could be extinguished by asteroid impacts, volcanic eruptions, or our own mistakes. It's empowering because it reminds us that we are the universe's only known way of valuing itself. It's The constraint also creates a different kind of hope. Instead of hoping for impossible breakthroughs that would allow us to travel to the stars, we can hope for achievable advances that would allow us to fully inhabit our solar system. Instead of hoping for contact with alien civilizations, we can hope for deeper understanding of our own civilization. This hope is more realistic and therefore more motivating. It's easier to work toward goals that are difficult but achievable than toward goals that are impossible. The constraint transforms our dreams from fantasies into projects, from wishes into plans. In wishes into plans, perhaps most importantly, the constraint allows us to find peace with our place in the universe. Instead of constantly yearning for what we cannot have, we can learn to appreciate what we do have. Instead of feeling trapped by our limitations, we can feel grateful for our opportunities. The solar system is not a prison. It's a playground. It's not a limitation. It's a laboratory. It's not a dead end. It's a beginning. When we fully accept our constraints, we can begin to see them not as barriers, but as the boundaries that define our cosmic kingdom. The transformation from feeling trapped to feeling free within constraints is not just psychological, it's philosophical. It represents a fundamental shift in how we understand our place in the universe. Instead of seeing ourselves as failed galactic explorers, we can see ourselves as successful solar system inhabitants. This shift in perspective doesn't deny the reality of our constraints. It transcends them. It doesn't pretend that we can travel to the stars. It realizes that we don't need to. It doesn't ignore our cosmic loneliness. It finds meaning in our cosmic uniqueness. The freedom we find within constraints is not the freedom to go anywhere. It's the freedom to be fully present where we are. It's the freedom to appreciate our cosmic kingdom, to develop our unique civilization, and to fulfill our role as the universe's only known way of experiencing itself. 2. In accepting our imprisonment, we discover that our prison is actually a palace. In accepting our limitations, we discover that our limitations define a realm of infinite possibility. In accepting our constraints, we discover that constraint itself can be the ultimate form of freedom. When we shift our perspective from cosmic expansion to cosmic appreciation, the solar system reveals itself to be not a prison, but a treasure trove of unimaginable wealth. What seemed like a tiny cage in the vastness of space is actually a kingdom rich beyond measure, containing resources, environments, and possibilities that could sustain human civilization for millions of years. Let's begin with the most obvious treasure. Energy. The sun, our local star, pours out 3.8 cores 10 circumflex, 26 watts of power continuously. That's more energy every second than human civilization has used in its entire history. Even if we could somehow capture just 1/10 billionth of the sun's output, we would have more energy than we could possibly use. The numbers are staggering. The sun produces more energy in 1 hour than humanity consumes in an entire year. If we could develop efficient solar collection systems, perhaps massive solar arrays in space, or a partial Dyson sphere around the sun, we could power a civilization 1 billion times larger than our current one. This energy wealth transforms everything. With unlimited clean energy, we could terraform planets, create artificial atmospheres, and maintain comfortable living conditions anywhere in the solar system. We could power massive manufacturing systems, support enormous populations, and pursue projects that would seem impossible with our current energy constraints. The material wealth of the solar system is equally impressive. The asteroid belt alone contains more metal than humanity has ever mined. A single metallic asteroid could provide more platinum than has ever been extracted from Earth. The total mass of the asteroid belt is roughly equivalent to 4% of the Moon's mass, but it's distributed in millions of separate objects that are far easier to mine than planetary surfaces. The moons of Jupiter and Saturn represent another form of wealth. Water, Europa, Enceladus, and other icy moons contain more water than all of Earth's oceans combined. This water could support vast populations, provide fuel for fusion reactors, and enable the growth of crops and ecosystems throughout the solar system. The diversity of environments in our solar system is breathtaking. Mars offers a familiar terrestrial environment that could be terraformed over time. Venus, despite its harsh conditions, has a thick atmosphere that could potentially be modified and an orbital zone that could support floating cities. The moons of Jupiter and Saturn offer exotic environments with unique properties: low gravity, methane lakes, subsurface oceans, and complex chemical systems. Each of these environments could support different types of human civilization. Mars could become a world of underground cities and domed habitats. Venus could host aerial colonies, floating in the more temperate upper atmosphere. The moons of Jupiter could become research stations and mining outposts. The asteroid belt could be home to a spacefaring civilization that never needs to live on planetary surfaces. The solar system also contains vast amounts of space itself. The volume of space within Neptune's orbit is so enormous that we could build millions of space habitats without crowding. These habitats could be customized for different purposes, some for manufacturing, others for research, still others for pure living space. O'Neill cylinders, proposed by physicist Gerard O'Neill in the 1970s, could house millions of people in Earth-like environments. These rotating habitats could provide artificial gravity, controlled weather, and landscapes designed for human comfort. They could be built to any specification, creating environments that are more pleasant than anything found on natural worlds. The wealth extends beyond materials and energy to opportunities for scientific discovery. Each planet and moon in our solar system represents a unique natural laboratory. Mars could teach us about planetary geology and the history of life. Venus could reveal the secrets of atmospheric dynamics and greenhouse effects. The moons of Jupiter and Saturn could show us how life might emerge in exotic environments. The solar system is also a vast library of natural history. Every crater, every rock formation, every atmospheric phenomenon tells a story about the formation and evolution of our cosmic neighborhood. We could spend millennia studying these records and still discover new insights about how planetary systems form and evolve. Perhaps most importantly, the solar system offers something that no amount of interstellar travel could provide: permanence. This is our home, our kingdom, our domain. We don't need to worry about maintaining supply lines across impossible distances or communicating with Earth across light years of space. Everything we need is here, within our cosmic neighborhood. The solar system also offers the possibility of backup and redundancy. If we spread human civilization across multiple worlds, we could ensure that no single catastrophe could destroy our species. An asteroid impact on Earth couldn't affect colonies on Mars. A volcanic eruption on Mars couldn't impact space habitats in the asteroid belt. A solar storm couldn't destroy underground cities on the moons of Jupiter. This distributed civilization could be more resilient and more diverse than any single world civilization. Each environment would encourage different approaches to technology, culture, and social organization. The low gravity of the moon might produce a civilization of engineers and artists. The harsh environment of Mars might create a culture of innovators and survivors. The orbital habitats might develop societies based on cooperation and careful resource management. The wealth of the solar system is not just material, it's cultural and intellectual. The diversity of environments would create a diversity of human experiences, leading to new forms of art, literature, philosophy, and science. We could have a civilization that is both unified and diverse, both stable and dynamic. When we truly appreciate the wealth of our solar system, our cosmic imprisonment begins to feel less like a limitation and more like a gift. We have been given a kingdom vast enough to explore for millennia, rich enough to support unimaginable civilizations, and diverse enough to challenge human creativity for millions of years. To truly understand the opportunity within our cosmic constraints, we need to grasp the vast timeline available to us. Human civilization is only about 10,000 years old. Written history spans merely 5,000 years. The entire history of our species, from cave paintings to space stations, has unfolded in less than 200,000 years. But the solar system offers us a timeline that makes our entire past seem like a brief moment. The Sun is currently about 4.6 billion years old, roughly halfway through its main sequence lifetime. It will continue to burn steadily for another 5 billion years before beginning to evolve into a red giant. But even this enormous time span is just the beginning of our solar system's story. As the Sun ages, it will gradually become brighter and warmer. In about 1 billion years, Earth will become too hot to support life as we know it. But this doesn't mean the end of habitability in our solar system. It means the expansion of habitability. As the Sun brightens, the habitable zone will move outward, making Mars more comfortable and potentially warming the moons of Jupiter. When the Sun finally exhausts its hydrogen fuel and begins to expand into a red giant,
It will temporarily become hundreds of times brighter than it is today.
this phase will last for several 100 million years, longer than complex life has existed on Earth. During this time, the outer planets and their moons will become warm enough to support liquid water and possibly life. After the red giant phase, the Sun will eject its outer layers and become a white dwarf, a small, dense star that will glow steadily for trillions of years. White dwarfs cool slowly, very slowly. Our Sun's white dwarf remnant will continue to provide heat and light for longer than the current age of the universe. This gives us a trillion-year timeline to work with. To put this in perspective, if the entire history of the universe so far were compressed into a single year, a trillion years would span more than 70 years. We have not just geological time to work with, we have cosmological time. Within this vast timeline, we could develop technologies that seem impossible today. We could learn to control matter at the atomic level, manipulate energy with perfect efficiency, and perhaps even influence the evolution of our star itself. We could become a technological civilization so advanced that our current science would seem primitive by comparison. The trillion-year timeline also allows for the possibility of true sustainability. We could develop closed-loop systems that recycle every atom, harness every photon, and waste nothing. We could create a civilization that exists in perfect harmony with its environment, using resources without depleting them. This timeline transforms our perspective on human potential. Instead of seeing ourselves as a brief flash of consciousness in an indifferent universe, we can see ourselves as the beginning of a cosmic-scale story. We are not the end product of evolution. We are the first chapter in a trillion-year book. The timeline also allows for unimaginable cultural and intellectual development. We could develop philosophies that take millennia to formulate, create art projects that span geological ages, and pursue scientific investigations that require millions of years to complete. We could become a civilization that thinks in cosmic timescales. If you too severe to fears would have the fears with the mouse. Consider what we could accomplish in a trillion years. We could explore every world in our solar system in detail, understand every natural process, and perhaps even create new worlds to suit our needs. We could develop technologies for living in environments that seem impossible today inside stars, in the quantum vacuum, or in dimensions we haven't yet discovered. The timeline also suggests that our current problems are temporary: climate change, resource depletion, political conflicts. All of these challenges exist on timescales of decades or centuries. Over trillion-year timescales, these problems will be solved or become irrelevant. We will develop new technologies, new social systems, and new ways of thinking that will make current problems seem trivial. But perhaps most importantly, the trillion-year timeline gives us something that interstellar travel could never provide: time to become truly wise. Instead of rushing to spread across the galaxy, we could spend the time necessary to understand ourselves, our place in the universe, and our responsibilities as conscious beings. The trillion-year timeline transforms our solar system from a prison into a realm of infinite possibility. We have not just space to explore, but time to grow, develop, and become something unimaginably greater than what we are today. In accepting our cosmic constraints, we discover something profound. We are not prisoners of the solar system. We are its inheritors. This realization transforms our entire relationship with our cosmic neighborhood. Instead of seeing ourselves as trapped, we can see ourselves as chosen. Instead of yearning for distant stars, we can claim dominion over our own stellar kingdom. The concept of becoming lords of our domain is not about conquest or domination in the traditional sense. It's about taking full responsibility for our cosmic neighborhood, developing its potential, and becoming worthy stewards of its incredible wealth. It's about transforming from cosmic prisoners into cosmic gardeners. This transformation begins with a shift in perspective. Instead of seeing the solar system as a small cage in a vast universe, we can see it as a complete universe in itself. Our domain extends from the sun's corona to the edge of the heliopause, encompassing a volume of space so vast that light takes more than a day to cross it. This is not a small kingdom. It's a realm of unimaginable size and complexity. As lords of this domain, we would have responsibilities that dwarf any role humans have ever played. We would be responsible for the development of entire worlds, the creation of new environments, and the long-term sustainability of our civilization across cosmic timescales. We would be planetary engineers, system architects, and cosmic gardeners. The role requires us to think beyond current human capabilities and imagine what we could become. We could develop technologies that seem magical today: the ability to control weather systems, to terraform planets, to create artificial gravity, and to manipulate matter at the atomic level. We could become a civilization that shapes worlds the way we currently shape gardens. Mars could become our first major terraforming project. Over centuries or millennia, we could transform its thin atmosphere into a breathable environment, warm its frozen surface into a comfortable climate, and establish vast ecosystems that support millions of species. Mars could become not just a colony, but a work of art, a planet sculpted by human intelligence and creativity. Venus presents a more challenging but equally rewarding opportunity. We could develop floating cities that hover in the planet's upper atmosphere, where conditions are more Earth-like. Over time, we might even learn to modify Venus's atmosphere itself, reducing its greenhouse effect and creating a habitable surface. Venus could become our testament to the power of human ingenuity. The moons of Jupiter and Saturn offer opportunities for even more exotic forms of development. Europa's subsurface ocean could become a vast aquatic ecosystem, populated by life forms designed for the unique conditions of that environment. Titan's methane lakes could become the foundation for a hydrocarbon-based civilization, unlike anything on Earth. The asteroid belt could become our industrial heartland, a vast manufacturing complex that provides resources for the entire solar system. We could establish mining operations, refining facilities, and manufacturing centers throughout the belt, creating a spacefaring civilization that never needs to depend on planetary surfaces. But our role as lords of the solar system extends beyond mere development. We would also be responsible for preservation and protection. We would need to ensure that our development doesn't destroy the natural wonders of our domain. We would need to preserve the beauty of Saturn's rings, the majesty of Jupiter's storms, and the delicate balance of planetary ecosystems. This responsibility extends to the protection of our domain from external threats. We would need to develop planetary defense systems capable of deflecting asteroids, monitoring solar activity, and protecting our civilization from cosmic hazards. We would be not just developers, but guardians of our cosmic kingdom. The role also requires us to think about the far future. As lords of our domain, we would be responsible for ensuring that our civilization can survive and thrive across the trillion-year timeline available to us. This means developing truly sustainable technologies, creating backup systems for critical infrastructure, and maintaining the knowledge and wisdom necessary for long-term survival. We would need to become masters of closed-loop systems, recycling every atom and every joule of energy. We would need to develop technologies that can maintain themselves across geological timescales. We would need to create social systems that can preserve human values and knowledge across cosmic time. The transformation into lords of our domain would also require us to develop new forms of consciousness and identity. We would need to think like immortals, plan like gods, and act like the stewards of worlds. We would need to expand our sense of self to encompass our entire solar system, to feel responsible for its welfare and proud of its achievements. This expanded consciousness would transform human culture in ways we can barely imagine. Our art would be created on planetary scales. Our architecture would span solar systems. Our music would be composed for audiences living across dozens of worlds. Our literature would tell stories that unfold across millennia. Science would become a cosmic endeavor, with experiments that span centuries and observations that require coordination across the entire solar system. We would have laboratories on every world, observatories in every orbit, and research stations in every environment. Our understanding of the universe would be based on direct experience rather than distant observation. Philosophy would grapple with questions that only immortal civilizations can explore. What is the meaning of existence across trillion-year timescales? How should conscious beings relate to the cosmos that created them? What are our responsibilities to the universe that gave us life? The transformation into lords of our domain would also give us something that interstellar travel could never provide: a sense of home. No matter how far we spread within our solar system, we would always be in our own neighborhood. We would always be connected to our origins, always be part of the same cosmic family. This sense of belonging would create a stability and continuity that wandering civilizations could never achieve. On the Reef, we'd be able to build institutions that last for geological ages, create traditions that span cosmic time, and develop a culture that is both ancient and eternal. In becoming lords of our domain, we would discover that our cosmic prison is actually a cosmic paradise. We would find that our limitations are actually our liberation. We would realize that being trapped in the solar system is not a failure of human ambition. It's the fulfillment of human destiny. We are not meant to be galactic wanderers, scattered across the cosmos and lost in the vastness of space. We are meant to be solar system lords, masters of our own cosmic kingdom, gardeners of worlds, and stewards of the only known oasis of consciousness in the universe. Our domain awaits, our kingdom beckons, our destiny calls. And so we arrive at the end of our journey into cosmic reality. We set out, hoping to find escape routes from our solar system prison. Instead, we discovered that every door is locked, every window is barred, and every dream of interstellar travel is crushed by the fundamental laws of physics. The speed of light stands as an insurmountable barrier. Energy requirements grow exponentially beyond all possibility. Exotic physics offers only false hope. Biology rebels against the journey. The universe itself seems designed to keep us trapped. But, in our prison, we found something unexpected. Freedom. Not the freedom to roam the galaxy, but the freedom to fully inhabit our cosmic neighborhood. Not the liberation of endless expansion, but the liberation of deep appreciation. We are not failed galactic explorers. We are successful solar system inheritors. We are not prisoners of physics. We are lords of our domain. The universe has given us a trillion-year timeline, unlimited energy, and resources beyond measure. Whole. It has given us worlds to terraform, moons to colonize, and space to fill with the greatest civilization ever imagined. We are trapped in the solar system forever, and perhaps that's exactly where we belong. What aspect of our cosmic imprisonment strikes you most deeply? Are you troubled by our limitations or inspired by our possibilities? Share your thoughts in the comments below. If this exploration into our cosmic constraints has sparked your curiosity, there's so much more to discover. The universe may have trapped us in our solar system, but it's also filled our cosmic neighborhood with endless wonders waiting to be explored. Ready to continue this journey of discovery? Click here to explore more cosmic mysteries, or browse our complete collection of space documentaries. The cosmos is vast, mysterious, and magnificent, and every question leads to new revelations about our place in the infinite.